Sir, good morning.
Good morning, sir. Good morning.
ना एमटेक टाइप बोलिया हां एमटेक टाइप बोलिया जोटा
बैक टा कर दिल दुकाई से जो एमटेक दीटा पिला से
अच्छा बैक थर्ड बैक थर्ड 15 हां एटा सेट 2
सेट 3 आगे सेट 1 टा ऊपर पड़ी तो એટલે चेंज ହେଲା So good morning one and all, and welcome to today's session. So this is day 2 of the GIAN session. This is session number 3. So yesterday we have seen Professor Barni talking about things like adversarial learning, what exactly it is, why it is required, all those stuff. The motivational part he has talked about yesterday. So I'm just going through this quickly, and let us start from the place where we left yesterday. So this is what was done in yesterday's class by Professor Barni. When he took this session, he introduced you, give you the motivation for adversarial signal processing and machine learning. He linked it up with game theory. Then he talked about mathematics. So yesterday I have also sent you, Professor Barni sent me in the late night all the slides. So I have emailed everything to the participants, as well as today's slides also is been emailed. So today he is going to talk about the source identification game, which even as I told yesterday also, that I am also a learner in this, so I'll also be very eager to hear him. So coming to my part, so yesterday we had just started with this, wherein I explained the basics of machine learning. So I took a very basic session. After that, we have gone ahead with some Colab notebooks. So iris petal dataset is what we have seen, and I have shown you how do we do it with Colab examples. Then we will go a little bit, I think 3 classifiers we have done. So we have done yesterday simple decision tree, then we have done our regression, right? So after that we have done SVM. So these are the 3 things that we have done. So our session went till 8:45 yesterday evening. So today's session is planned to for this an important part again. So if you really wanted to go into deep learning, you should have simple knowledge of these terms. So our focus today is to introduce you to all these architectures and all these stuff again from the simple point of view. So I am here in day 2, right? Session number 4 in the means in the sense it is 3 in the sense that the 2 sessions have taken place earlier. So let's go ahead with this again. Before we go to the slide and the Colab notebooks, I'd like to thank my students here again, all these set of students who have been behind this notebooks, all of this. So So this is my habit that every class I start, whoever has helped me, I acknowledge them and give them their due credit. So let's go quickly to what was planned today. So today, what is planned will go like yesterday itself. So we will try to understand things again from a general point of view, because today we are getting introduction into this CNN. So many people have this notion, they have difficulty in understanding CNN. They always, I keep getting this comment that CNN is, we don't know, it's like a black box. We don't know what is happening inside. So I don't like to use it. So many things I am trying to I just get whenever I talk about machine learning, deep learning here and there. So, but it is easy, provided we get a proper understanding for that. So let's spend. So today's session, as I have told, starts from 9:30. It is up till 12. So initial an hour. Let us, like we yesterday we did. We started with basics of ML, wherein I told you simple examples of convolution, for simple examples of convolution matrix. So along with confusion metrics, I told you how to I linked it up with an analogy with real life example. Today also the target will be the same thing. Introduce you to this machine deep learning, etc. Because we have kept on using these AI, ML, DL everywhere. Then we get confused what it is. So one has to have a clarity. Though we can code, I have seen many middle level or experts knowing many things to code, but they don't know the basic concepts. So as teachers, our basic concept is to tell the students or the participants clarity on these concepts is very important, because if that is known, then we get to know easily other things. So our talk starts with this today, that AI, machine learning, deep learning, what exactly it is. So before we go here, so this Ian Goodfellow's book of deep learning is there, because it's a standard book. That's why I am referring it as a reference material. So here it's not a textbook, it's a reference material where many people use it across the ML/DL fields. Hence on for onwards, I'll be using the word ML for machine learning, DL for deep learning. So deep learning Goodfellow's book is there, so you could get a copy, and Indian edition is also there. You can always have a copy of this for reference. So coming to what exactly is this? So we have been see, it is just like I give the whenever I take these talks of MLDL AI, I give try to give analogies. So I start giving the analogy that we are in very bad times, in the sense that COVID has come and it has started from early 2020, and we are now in early 22. So it came in three waves. In India, at least, it came in three waves: wave one, wave two, wave three. And we have seen the effects, the bad effects of the COVID. Similarly, here I keep the analogy that even AI, ML, DL has come in three waves. So here, let me annotate this particular part and try to tell you the basics of this. AI means early, it was an early excitement where some robots were built. The Japanese were the first people to start AI, in the sense their robots started moving. Maruti Suzuki is a very good example where they were trying to make the cars, and the cars were not being manufactured or assembled using people. People were there, but not many, not that many people. You had robots which were fixing, only overseeing was done by people. So the early AI excitement, which I call the first wave. So this is the first wave which is there for our field. The first wave started early 50s, 50, 60, 80s. Though it came to India a little bit late, the wave started early, that in the sense that people started getting excited that robots are going to do the stuff what the human beings can do. So this stirred excitement that yes, AI is one field where it is artificial. The name itself says it is not a human intelligence. It is an artificial intelligence where we are trying to tell somebody what to do, right? So who tells? Again, the programmer. So many programmers came up. So there was a view that everybody started learning programming. All of us know of that generation who are belonging to 80s and 90s. We have seen this particular generation. So what happened after this? Yes, we were having some of the robots which could do the job, but they were not enough, or we did not have big. We had big robots, but we didn't have miniaturization. So after that came machine learning, where people tried to tell the computer or a small device like an Arduino, etc., what to do. So by feeding data. So data was the important part for that, and then you had that wave. So this came in early 90s. So if you could see this here, 90s, it began here, which came the second wave. So here after the early excitement of AI, you came under a second wave where machine learning begins to flourish. I'll take few examples later exactly what, but I'm on this slide, so let me not go ahead. So machine learning ruled here till around 2010, if you could look, 2010 to 2012. So when I say this is for the entire world, but in India always we get 4 to 5 years later because of the science and technology that we are having the investment which is very less. So that's why we get 2 3 years later. So coming to next, here came around 2010, early deep learning started to go. So we had a third wave here. So please compare these parts to the waves what we have gone through, because you will easily understand. Because if I say first wave COVID, you will say that it was somewhere in September October of 2020. Second wave you will tell April May June. Third wave you will say it was somewhere December January, and it is now going on, it's going to end. So here this is what we compare with our real life example. So deep learning started around 2010 2012, and now we are having we are somewhere here. So where we are here in 2022. Okay, so this is what is the graph that we have, which is telling. So it is like a subset on top. So DL is also a sort of AI, ML is also a sort of AI. So it's like if you take it from a set point of view, from a mathematics point of view, you have a big set. Inside that you have ML, and inside that you have deep learning. I'll clarify what exactly is the difference between ML and DL a little bit later. So as we go here, so here what we see, general artificial intelligence means what? The robots can do, the computers can do whatever we can do, right? So it mimics human intelligence. So here we have that sense that, see here I have written whatever is the slide. This is borrowed from the source. So where it is saying that human intelligence is being mimicked. So the computer thinks as if we think. So this is the general AI. This is a broad subset, right? Now it is narrowed down. So somewhere as we saw that early 90s, 1990s came this field where we came into machine learning. So in machine learning, what we could see, you would have heard that, I think you have heard that these chess games, Grandmaster Gary Kasparov or Vishwanatham Anand is playing with a computer. The chess game is being played with the help. Who is the opponent of Gary Kasparov or Vishwanatham Anand? It is a computer. So you would have heard somewhere in 90s, early 2000 that Vishwanatham Anand became a grandmaster by defeating the fastest computer. So this is what became in machine learning. That will come a little bit later. What exactly it is, how it is. So here we can say that machine learning was that area where computers were trained, machines were trained to do broader than narrower things than what AI did. So the task was very narrow in the sense playing chess, doing this, doing X, playing games, right, solving some difficult problems, all this particular part. So coming to this, uh, so I request the participants to just mute their mic. Yeah, the administrator, please, you could mute the mic. Yeah. So I think this is where it was, where we were into 1990s and ML started coming. So machine learning, as I'll compare it with yesterday's evening session. So yesterday we have done support vector machine, right? Yesterday we have done logistic regression. Yesterday we have done our this decision tree classifier. So three classifiers we have done. So yesterday what we have done is nothing but your machine learning. What we have done, just started with machine learning where we talked about three class. None of them used neural networks. None of them used yesterday's examples. None of them used neural networks. Decision tree did not use neural network. Then we had this SVM which did not use neural networks. So machine learning is very broad in the sense you can have SVM, you can have some other classifiers like whatever decision tree, random forest, many classifiers are. Naive Bayes theorem is there, Bayes theorem. All these things, if you are doing to solve some task, whatever may be your task, if you are doing that, then you are entering into the area of ML. So you are doing machine learning. And now Yesterday also I have told you an example of a perceptron where I told you how it learns, how it is starting to learn, how it is learning the weights. Example, I have two examples I have given. XOR problem I have given, and yesterday going to a movie problem I have given. So example I have given where you can learn how you can update the weights. So that weight learning is done with a neural, or yesterday we have seen two layer, one hidden layer was there, which is nothing but your neural network. So if you are using only neural networks, no SVM, nothing, right? Then you are slowly moving down into becoming more narrow like this. Neural network means if you are only using neural networks to achieve a task, then you are slowly moving down something called deep learning, right? So one neural network yesterday I have shown you for XOR. So there may be thousands of neural networks here. So if it goes very deep, that it goes very large neural networks are there, so hundreds and thousands of neural network are there, then you are going into a field called deep learning. So I'll go into this. So here the textbook definition is there here, right? So this textbook definition you can always read, but we will try in our task to just tell you the general parts so that you can understand it from a broader point of view. So I'll be also sharing these slides with all of you, and you can always read this later also. But if you want to take from thumb rule, AI very broad, machine learning subset of AI that only machines are doing some narrow jobs may be Netflix, jobs may be playing a game of chess, no, jobs may be any mundane stuff. Now you want to do specific things using only, you found out that neural networks are very good, you want to use them, then you are going into something called deep learning. So I'll go a little bit later here. So let's go and understand what this traditional part is. Okay, so the traditional part is called machine learning here. So machine learning, what is traditional programming? So this is the programming that we used to do when we started our part. I think there is a lot of disturbance. I'm requesting the participants to mute your mic, please. Since I'm taking a session, the control is not with me. I'm requesting again to mute your mic. Yeah. So the traditional programming had what? We had data, you were writing a program. So all of us wrote this program who came from olden days, C program, C++ program, we wrote CPP. Then people told that no, these are all old, we'll write Java, right? So we were trying to write some program. We were of course giving data. Without inputs, nothing works. And we were getting some outputs. So this was a traditional programming approach what we had. So all of us have done this particular part of doing a traditional programming where we got feed some data, write a program to solve the problem and get some output. So this is what we have done, and computer does this, of course. But in machine learning, it is a role reversal. So what we do here is output we give as an input here. So we tell that this is the output, this is the label, this is A, this is B, right? This is how a pawn moves, right? This is how an elephant moves in a game of chess. This is how a bishop moves. So we are telling the output to the computer, and we are not writing programs. So yesterday also you have seen we have not written any programs. We have used only some classifiers. We have given a data. Again, see the underlying assumption is data. Everything important here is data, that without your data you can't do anything. So if you minus data from machine learning or AI or your deep learning, your models are of no use, right? So we give a data, so it's just flipped out. The output here we try to bring as an input here. So once we bring the output here and we tell the class that supervised learning, if it is supervised learning, then I will tell that this is A. We give thousands of examples of A and then tell the computer you learn, right? So we tell that this is the label A, and in the data we give 1000 examples of A. So if I'm trying to do this, with the help of a computer, then the classifier is trying to build the boundary and give the solution. The program is not written explicitly just as we wrote for I is equal to 0, whatever we were writing in earlier days. So that is minus off. So that is easily minus off. So it's just a role reversal from the traditional to the machine learning language. This is how it is. So if anybody asks you how it is, you should be able to tell what is machine learning. Two things which are important in machine learning. One is your data. underlining data, whatever you have. The more data you have, the better in general thumb rule, but not necessarily. When we go ahead, we'll go into understanding why not so. But to your beginner level, when you are starting a course, you can say that yes, for a machine learning algorithm, you should have good data. Then along with that, you should have good labor, you should have good domain knowledge of your problem. Then your computer will solve your problem. It can be trained either via supervised learning, and so we'll go into that slowly. So this is where we start. Machine learning is like this, where you can, so what are the things which you can use here? You can use your SVM. It is a machine learning algorithm which we have done yesterday. So yesterday you can use the decision tree. I'll write DT, decision tree here. Then along with this, you have also used some logistic regression, you may use some simple perceptrons. Perceptron also you can use. So you can use many algorithm depending on what is your task. Everything comes under machine learning, broad. So come back here. Everything is this machine learning. But now, yes, SVM is not good. Decision tree is not good, right? Only I am going to use this perceptron, and I am going to make it better. I am going to use only neural networks. Many neural networks I am going to use. Then we go into a field. Then we go into a field which is called deep learning. So deep learning is only using neural networks. Keep that in mind. Deep learning is not using any SVM, right? So this is the broad definition that we have from machine, AI, as well as DL. Many people get confused. So if I summarize all these things, I can just say that you can, broad AI is everything, right? Any and everything, even mechanical sciences, all things, all are AI only, wherein you're having robots to do your job, machine, etc., to do the job. It's AI. Anything which is having intelligence is AI. Now coming to machine learning, you are using vice versa approach than traditional programming, coming back here and feeding data, giving its output labels. Computer is generating the program, building the boundary, etc. Then you are specifically in machine learning, right? Then in machine learning, again very broad, you can have all these classifiers, you can have neural networks also. But if you subtract SVM, decision tree, random forest, all these people, and say no, I am neural network is the best, I am only going to use neural network, then you are entering into deep, right? So why it is called deep, I'll tell a little bit later, but this is how yours comes. So the arrow mark goes like this, from broad to narrow. So we are now in the deep learning era, where any and everything nowadays is DL. So deep learning, so AI, right? ML, like this, ML. So neural network, I have written here neural network based DL. DL doesn't encompass SVM, right? So neural network based DL, everything in DL is neural networks, lot of hidden layers, lot of parameters. So with this we move ahead, right? Why it started, how it started, that we will try to understand today and tomorrow. It started from images, because the image processing field was having this image, where you have this two dimensions. So all of us know images of two dimensions, X and Y. So this is dimension here, one dimension here, the other dimension is here. So here I have plotted dimension 1 down. So here I have plot dimension 1 here, dimension 2 here. And what I have plot, one small patch I have taken. Please see the data. One small patch I have taken and blown off here. So as we know, this is a black and white. See, this is Lena image, it's black and white. So if you plot this, even you can use a simple MATLAB. You can see row column. This is first row number 1, column number 1. So what is the value here? 183. So this is technically, this physical quantity is called intensity with regard to your image, 183. So first row, second column. So here I am first row, second column. The item number is 160. So this 160 I am plotting here. So this is a physical quantity. So need not necessarily be always image. You can also take temperature. So today's date is 15 February, right? Today's temperature at Rourkela is around 18 degrees now, 17 to 18 degrees now. So your physical quantity can also be temperature. So please understand that if anybody here is joining from other fields, it's not necessary that any and everything is image processing, right? So today you want to take the measurement of my blood pressure. What is my blood pressure currently? Then your dimension, your physical quantity will be blood pressure. Okay, in its standard range, of course. So here we are taken an example of a two-dimensional signal, It's an image. Technically, we call it as image. It's a 2D signal, right? And what are the two dimension? Dimension one is like this. Dimension two is like this. So row column, row column, and whatever is inside this is physically called intensity level, or it is also referred in image processing literature as gray level or intensity. So one should know this because we are going ahead with this. Deep learning requires image processing. Started with this deep learning started with image processing, but nowadays it is used for natural language processing, Twitter analysis. Then we have so many examples. I will go, but since it started from here, it's my duty to tell you what exactly is an image. Okay, so now all of us have heard about this convolution neural network. So it is our duty. It's very important here. If you do not understand properly what is convolution, then anything in machine learning or deep learning you do, it is of no physical significance because typically you don't know what is a convolution. So I always tell here, please put all effort and understand whatever I am trying to say here. What is a convolution? So come back, this convolution, even if there are some computer science participants here, please understand that this is a traditional convolution. We will try to explain it with a nice graph here, whatever I have, so that it becomes easier. Suppose you have not heard at all what exactly is this, you should be able to get exactly what I'm trying to say. So here, let us go into the traditional convolution. So here I am having something called a mask. Okay, so here I am having a mask. It is also called filter. It is also called template. Three names are there, right? Then I have an input, which is an image, right? So how do I calculate convolution? So you see the size of this. There are two rows. There are two columns. So the convolution filter or mask B has two rows, two columns. So two rows here, two columns here. Then your image here has four rows. So 1, 2, 3, and 4. Four rows, and you have four columns. 1, 2, 3, and 4. So 2 cross 2 mask, and you have 4 cross 4 columns with regard to the image. Now what we do? This is what we do. See here what we do. Pictorial representation I take, right? So I keep this on top of this. Superimpose. So when I superimpose this, let us go back. Let us go back here. I superimpose this block on the first part. So here I am superimposing it here. So this is what is shown typically here. When they sit on top of each other, we'll see what to do. So let's go back here. So when you see this, what happens? B is superimposing on this. Now what you have to do? You have to do element wise multiplication. So what you have to do, A11 is multiplied by B11 because they are superimposed. Next, A12 is superimposed on B12. Similarly, down part 21 is imposed on 21, and this. So you got superimposed, you have to do mult here. You have to do multiplication. Now you have to go forward, slide it. So you have to go forward here, you have to slide this. So here what we get, so this is the C11, whatever we are getting. So here we add all this. So here we add this, all these values we are adding like this. All of these values we are adding. So here we add like this. So we get the C11. So let us go back here. So I'm just going back to tell how we got this. We got C11. So how we got C11? By superimposing here this on top, element wise multiplying these two people here, and these two people here, and taking the summation. So we got C1. So here let us put this into picture back. So I'll be a bit quick. So this is what we do. We added all this here, and we got the first element. Very important here, right? So we take a typical example here, whatever we did, like this, we continue this process. So now we take real numbers. So let us do this. -1 multiplied by 4, 2 multiplied by 4, -1 multiplied by 4, 2 multiplied by 3. Quickly you add this, you see what you get. Okay, so you get 6. If you want to do, I can just do here -1 multiplied by 4, here multi with 4, right? Then plus, you get 2 multiplied by 4, 2 multiplied by 4, plus, I'm doing it for one value. Next, -1 multiplied by 4, -1 multiplied by 4, Okay, plus multiplied by 2, 6. 3 multiplied by 2, 6. Right? So 4 2s are 8 goes. This is minus 8 goes. So 6 remains. 6 is put here. Now what you have to do? You have to go forward. You have to multiply the next. Right? So you slide. You slide and you next multiply -1 with 4. Then you multiply 2 with 7. Then you multiply -1 with 3. So with this block you multiply. With this block. Next block. Then you will do, right? So you get 23. Then you again move ahead like this. Take this block multiplied with the same filter here. You get 21. Come down here. Take this block, right? Multiply with this. Get one more result, 9. Then you do this. You get 26. Then with this next one. Then again you go ahead. Slide it. You get 19. Last row, come here, multiply with this, check all the answers are right or not. Then you get this 16. After that you slide here with the next you get 27. Then the last one you take here, multiply with these numbers, add it, you get 17. So this is what is convolution. So convolution is what? Multiply individually when it slides, you multiply individually, take its sum, fill the value. Then what? Take this mask and slide it to the next part of the. So this is convolution. Very important. Very this small principle which I have explained with 2 by 2. Simple 2 by 2 mask is used in all neural networks. So whatever you are called convolution neural network, neural network, whatever it does, it is doing as simple as this. As simple as this. So here it's very important here to tell you this. So I just stop little bit here to ask, because we want clarity on this to the participants. If there is any issues, we will get it cleared here, or else we'll of course go ahead. Okay.
Here boundary, how to take boundary? I will ignore boundary.
Yeah, we can. Yeah, as he rightly said, how to take the boundaries. Currently, we assume that these boundaries are either 1 1 1 or 0. We ignore it.
Because now in the normal convolution we assume boundary.
Yeah.
And we will process. Here we are not considering the boundary.
Yeah, we are not considering the boundary. So we are leaving
so that
the
is
boundary.
The change compared to the convolution conventional.
As compared to conventional convolution, this is similar, but we have just ignored the boundary, because later I will come when we tell we are having a very big task here. See, even if I want to explain this, I took around 15 minutes, right? If you see, I took this slide, I went up, right? If I do page up, I have gone back step by step. Then again I have explained. I took around 15 minutes. So now you assume how much time neural network will take for an entire image. Okay, so it is 1024 what will be the computations? How many numbers will be there, right? So though I took 15-20 solution, even neural network, when it is doing this, it takes a lot of time. That we will come to that slowly. Everything is linked one by one. So it is good that you are asking me that what about boundary. Currently what we are assuming that we are neglecting the boundaries. We don't have boundaries. So let us keep simple assumptions. Take to take this, slide it over this particular image, and go on doing the element wise multiplication, addition, going on filling this table. This is what we do, right? So this convolution comes from electronics, please understand. Moreover, it comes from mathematics, but convolution is being used in electronics. But majority of the convolutions are being used by computer science data scientists. So there is no boundary as such, though classifier builds boundaries. There is no boundary as such. This is mathematics, this is electronics, this is computer. Nowadays, everything is interdisciplinary. So I have taken now a convolution numerical example. Let us link it and show. I think this is traditional image processing. So if I take one of the filters, so this is one simple filter I take. I keep on this image. How I keep? Here I keep, calculate the value. Next I slide, whatever I told you. I slide here, I calculate the value. I slide here, I calculate the value. I go on doing it raster scan wise. Here like this, I go on doing like this. Then I go till here. Once I do this, and if I use this mask like this, some like this mask, then what I get is this. You see what you have got. You have got the edges. People who have done traditional image processing will directly tell me, sir, this is edge detection problem what you have done. Right? We are not talking machine learning. Please understand, we are not yet talking to machine edge detection we have done. And people who know a little bit of image processing will tell, sir, you have used a Laplacian mask. So you will say this mask is Laplacian. But my class now is for not a image processing person. It is a general machine learning task. So I am not going to tell you all these details. But this is, of course, we know only that this is a mask. So come back to our earlier problem. We have a mask, we have an input image, convolved image. If somebody asks me, what is the use of convolution? I should be able to tell. So the use of convolution is here edge detection. So here you can see there are edges. So next anybody asks me why you do edge detection? What is the use? Right? So I can give you an example. There is these what you call these biscuit factories. There is a camera on top. Biscuits which are ready-made biscuits are going here. If there is you will detect a biscuit packet which is rectangular. So you will detect edges, and there should typically be 4 edges at this much distance. If there is somewhere crack, then it means that that particular biscuit bundle is error. So you have to discard that. You cannot send it. So conveyor belt will have one camera. The conveyor belt is going, biscuit packets are going, chips are going, semiconductor chip. You are going to go on detecting edges, right? And whichever is having issues, that will be sent out. So it is automated. So edge detection is also useful. Many people who have done image processing knows why edge detection is useful. So here we have seen the cow's image here. Here we have seen traditional Lena. So if you use this and do this bit by bit, you will get this. Slide this, you will get. So this is convolution edge detection, traditional image processing. We are not talking about machine learning yet. So this was earlier also there. But how it came into machine learning, etc., that we will see. Right? And why this deep learning? So we are slowly from machine learning, we are coming slowly to deep learning using only this convolution concept. So let us come to this, understand this. So here I am taking an input, right? Here I am taking a mask. So my mask here is like this. I try to do this. So this is my mask. So I want to detect the beak. So I want to see whether it is a bird or not. So what I try to do, I try to do the, suppose this is extracted from this. So I am just taking this from this, right? So this image is something written here like this. This is what is the image, and this is the filter. Like this, there may be many filters. So what are these filters called? These are nothing but masks. This is the mask. This is the mask, and this is the original image. This is some image. So I'm taking example of image because it started from image processing. So image. Now what I do, right? So I try to do this convolution. So I try to learn this convolution. So how do I start? I am starting the demo. I took the first filter. I come here, I keep it on top. So this guy I'll keep on top of this. I element wise multiply. So I element wise multiply, which is called mathematically dot product, and I get 3. This is convolution which I showed earlier. So now I'm doing it for this. Next, I slide 1. So I slide on right on 1. So I go here 1. Again I do dot product, 1 multiplied by 0 minus 1 multiplied by 0. I do this and add it, which is called dot product. I do this, so I get next minus 1. So next I again go ahead, right? So I go on doing this job. I go on doing this, then I slide down. See, I slide down. I went on doing this till I went to my last, and I got this. So what I'm trying to say here is, traditionally in your feature learning, whatever you are doing, you are extracting some features. Yesterday, please recall what we are trying to do. We were trying to learn about cats and dogs. So what are the features that you are extracting? Skin color, fur, doors and windows, height, width, etc. Right? So we should have domain knowledge to do that. Here we don't. You only have to use convolution. You don't need to learn what features, whether I will extract color, whether I will extract shape, whether I will extract length, breadth. No, you are not going to do. Your convolution neural network will do it. So it is kind of making you independent of the features domain. So it is telling you that don't worry about feature, use a convolution neural network, and it will do its job. But what is that job being done? The job is being done is simple dot products. So what is happening here is, when I fix like this big 6x6 image is being represented by these people. These are the people who are represented. So you can take, again, I'm using common analogy. It is like your class CR. So you are around 100 people in the class. So you have 2 or 3 representatives for yourself. So they will represent you, right? Whatever use you have for 100 people, they will be conveying it to the higher authorities. So class CR, elected representatives, MLAs, MPs, they represent one full constituency. So it is like this. So this is your feature representation. And feature representation, you don't need to have domain knowledge. Now I don't need to know cat and dog. I don't need to know door and window. I don't need to know shirts. Yesterday, whatever example I have done, I don't need to know them at all. I only know to know that there is some concept called convolution, right? I take that, I keep it on the image, slide like this. I get some people here which are less. So here you see this was 6x6. This is not 6x6. This is 4x4, less number, right? So this is what is your convolution here. This is what we explain. So this is how it goes. So I finished my first patch. Now I can go on doing like this. I can go on doing like this. So what I'm trying to say here is, I can start with filter 2. So it's not necessary that only that filter I have to use. I can use filter 2. Filter 2 I repeat for each filter. So what happens? I get next representation. See here what you get. So I'm just quickly going through my slide. I get all these numbers. So I repeat this. So this, whatever convolved output I have got, is called a feature map. So here this feature map is independent of the domain. So, but yes, choice of filters you have to do, that will go a little bit later. How to choose that we will go. Here we are trying to understand what is convolution and what is feature map, right? And how we are getting this. So very important here, many people get confused. I have seen many people come to me and tell convolution is very difficult to understand. Answer is no. If you know it one by one. So what is one by one? Start from a mask, any mask, put it over an image or any of the data, go on sliding. So if you slide by one, this is called technically stride. So you will read in convolution or in your deep learning, stride equal to 1. Not necessary stride equal to 1. So you can make stride equal to 2 also. It depends on you. You are the designer. You are the person who is making the machine learning algorithm. That time what will happen? You will get less number of features here. You will not get that many number of features, less number of features. You will stride with 2. You can stride with 3, right? So you can start from 1, you can go 2. That is how you will tune your network. That is left to you as a parameter you can change. So when you read this convolution network, you will come across a term called stride. So here simplest stride which we use is 1, not necessary 1. You can make it 2, right? And what does the result of convolution give? Technically, we call it as a feature map. So let's go ahead here. Okay, so this see, this was 6x6. So this size was 6x6, and here I got how much? We use 2 filters, filter 1, filter 2. So we use 2 filters we used. So we got 4x4 matrix. Such how many matrix we got? 2 matrix, right? With 2 filters we got 2 such matrices. So now what we do, I'm just showing you what will happen with stride 2. Not necessary stride should be 1. You will get some different numbers, right? So here you see, instead of keeping here, I am keeping it here, right? Stride is 2. So when I get this, so this representation will be different. So you can always change your stride. Okay. So what will happen if it is color? This is for gray image, whatever I showed. What will happen if it is color image? Then your computations will increase. You have 3 channels, R, you have G, you have B. Then your computational will increase. Your computations will increase. Your RGB channels, you have to do it on each channel, right? So here now the size becomes large. So you have one R, one G, one B. Now you have to do this filter over all this, right? So here you have to go and you have to do this filter 1, filter 2. So your feature map will become large because it's a color image. If it was a gray image, it is easy, you can use one filter. But now you are different planes, you have to extract information out of, meaningful information out of it. This is what is the concept that we should do it for all channels, right? But process is same. Take filter, keep it on R channel, take filter, keep it on G, keep it on B. Get your feature representation, whatever we got earlier, right? So once we do this, once we do a convolution, so we took an image, see how I have done. We took an image, some example I have taken. I did convolution with two filters. I got some representation using some stride. I got some representation, right? I got some representation. So once we do this, finally, when we finish, we'll see one simple network a little bit later. So here, the convolution neural network, lastly, what we do, we connect all these values. We connect all these values to get our outputs. So we take this, it is present here. So here, this is what is present in green. So this is the representation, and we connect that and we do the results. So let's take this. So here, this is what we get. So this is how we get. So I'm just showing the same example. 3 we got, right? So this, the same 3 here. So here I write the same 3 here is written here. How we get it? See, I have arranged 1 0 0 0 1 0 0 0 1 1 0 0 0 0 1 like this. All data I will keep like this. Big data it is 6 cross 6, 36 numbers. So 36 people are being represented by, see, all these are connected. So all these 36 people will be represented by only these fewer parameters. So instead of having so many parameter 36, we are going to get fewer parameters. So here we come. So this is 3, then this is -1. They are representative. Then you get here 3 -1. So whatever we got earlier, then it is -3 gets here. So you have to connect. If we connect everything, the slide becomes very scrabby and it doesn't look good. So I have connected 2 people, 3 and -1. So like this, all the inputs, these were the inputs. The original image was an input. Now we have made a feature map and it is being represented by these fewer parameters. So now what is happening? These people are representing, they are representatives of this image. These people are the representative of this. Fewer parameters. So they are having fewer parameters. This is called weight sharing. Technically, it is called weight sharing. We are going to share the weights. So these are the people who are going to take the weight of all these people, right? So now what happens? So once we do this, see what we do this here, filter 1, filter 2, same example I repeat, same numbers I have taken. Filter 1, we get these values. Filter 1, we get these values here. So 4 cross 1, 2, 3, 4 like this. Filter 2, we get this. See, for small 6 by 6 image, you got these many numbers. What is the size of an original image? Anybody can tell me? Simple example, we took 6 by 6. See, my slide is fully over in the sense that everything is occupied. 6 by 6 image, this much. What is the actual size of any images, real life images? Anybody knows?
It's higher dimension.
A higher dimension. Can you give some example?
1024.
Yeah, always all of us are having phones, na? कहीं पे भी मिलता है तो हम photo खींच लेते हैं. So, and very small photo nobody likes, right? So as our friend told, he says, 124, 124, right? 1024 into 1024 size. This is quite common. But people will say, no, 1024, 1024, not for marriage photography. We require bigger, right? So 3096 HD images, cross 408, this 408 like this. Such images are there nowadays, HD images. Even normal phones nowadays take 512 is gone. 512, 720, cos 720 is gone. 512, nobody likes to see. What we do, we zoom and see this 512. So nowadays you see this, see 3096 and 40 HD, full HD, if you see, how many pixels are there? Lakhs. So if you take lakhs pixel, go on doing filtering, right? Even the fastest supercomputer will fail. You will say for one image gone. And how many images you are giving in deep learning? You are giving lakhs and thousands of images. When will it finish this? It will never finish this. But we want an end, we want a solution, right? So though these people are representatives, they are representing, right? Representing whom? This 6x6 image. Though they are doing that, but we cannot do it for, if my image is like simple yesterday what I have taken, it is okay. But if my real life images are very large, not okay, right? So what I should do? We should still try to subsample. So out of these people, again we should take better people who are best. We have to take the people who are best, right? Because so many computation you cannot do with these big things. So we come to the concept called max pooling. Pooling means, you are going to take best representatives, the best person. Why? Why you want to take the best person, best representatives? Why? Because you don't have space. All these people will clog your time, right? Memory. We have to be optimum. So we go to max pooling. So after convolution, we do pooling. So you will see, excuse me. So you will see later when I use a network, I am going to use pooling. So you would also heard about this pooling. What is pooling? Let us see. Let us take this 4x4. Whatever is my representative, let us divide this into 4x4. In this 4x4, I will take the best person by using the function non-linear function max. So max amongst these, and here also I will use the max. So max here will be 3. See, I go back. -1 is not max, -3 is not max, 1 is not max. Maximum among these 4 number is 3. So what I do? I choose 3. Right? Amongst this max is 0. Amongst this max is again 3. Amongst this max is 1. I repeat this, max is here, max is here, max is here, max is here. So now naturally one question will come to me here. People will ask me here, sir, by doing this, are you not losing data? Will this question be there to me? Answer is yes or no. Definitely it will be there to me. Are you not losing data? Answer is yes, I am losing data. I am losing the representative, right? So, but what can I do? What can I do? I have so big image. I cannot go on keeping the space or time for computing. I want less people. So what I try to do is I try to select the best representative. So obviously downsampling will lose data, 100% you will lose data, but it is going to take the best representative 3. So now my boxes will have 3 1 1 0 3 in place of earlier numbers whatever we had. One more question I will get. Why you used max, sir? So anybody told to use max? Answer is no. You are having average. Somebody may take, I will take all these 4 numbers. I will take all these 4 numbers, whatever was there. So let us go back. So I am going back here quickly. I will do 3 plus of -1 plus of -3 plus 1 divided by 4. Average. Do it. There is a concept called average pooling. There is a concept, there is a ready-made function of average pooling. And please understand, though I am taking 15 minutes, 20 minutes to explain each concept, right? All of these are one-line commands. All of these are one-line commands. But just blindly using this one-line command without understanding will not help you. If you want to be successful in this area, you should know what is the concept, right? So 2 questions I will get here. Will you lose data? Answer is yes. By subsample, this is some sort of subsampling. We are going to lose data, but we are going to choose the best person. So best person choice is either max pooling or average pooling. There are many other pooling techniques. Our course is not on pooling. So here what you should understand, after doing the convolution, you have to do pooling. If you do not do pooling, if it is a small example, don't do pooling. Not necessary. If you can afford not pooling, you can pull. Not pull, not necessary. It's not necessary that we should do pooling, right? So this is what it is. So I quickly go through a slide. Pooling means choosing the best representative. So same thing I have put here. Why pooling? Right? Subsampling will not change the object. So if it is an elephant, it will always remain an elephant. Right? If it is a cat, it will always remain cat. It will not change the object, but it will subsampling will lose some amount of data. So it is, see, if I take a bird and I subsample, subsample, then still I will get a bird. What I'm trying to say is still I will get a bird, but I may not get it an accurate. Accuracy is not required here because it is each convolution layer. All of them together will be acting. It's not one person, right? And real life images are not so small. They are 1024. Nowadays we are having 1024 even by a normal phone. 1024 cross 1024. Assume lakhs of pixels are used, right? So here we are doing why pooling, we should understand, right? So we are doing this pooling here. So I'm just skipping this. Okay. So here we are coming to this, why a CNN compresses a fully convolution in two ways. It reduces the number of connections. Shared weights I have shown you earlier. We do pooling to reduce the complexity. Please understand, pooling is only for reduction of complexity. If you believe for your problem pooling is not required, don't use. Are you getting this? But majority of the machine learning are so large that pooling will be required, either max pooling or average pooling, right? Then come here. So we show here what happens. So I do max pooling here, I do convolution, I do max. So what is my pipeline? I do convolution, then after doing convolution I come and do max pooling, then I come here. These are my best representatives. And what is this? This is reduced feature map. This is reduced. These are my features. I don't need to know the feature. Reduced, right? Features, feature map it is. This is reduced features. My actual feature was here. How did I do convolution? I used filters I used. This is how I did convolution. So I used a filter here. How did I use my this pooling? I chose some example max what I showed. Then I came to best representation, reduced feature, right? So this is a new image which is representing the same image, but it is smaller in size. Just like your example, what we had here. The same image, but it is smaller in size. So are we getting this? It still represents the same image, smaller. So here, this is our task here, that we come here, right? And we come, it's a new image, but smaller. Each filter is a channel, right? So let us come to the whole CNN. Together, let us see what we can do. So now it is a cat. See, it is a cat. Convolution I will do with cat. Some filters. So what is the thing required here? Filter. Suppose I use some 3-4 filters. How to use filter and all we'll tell a little bit later. Filter. I use convolution. I do filtering. Right? I get reduced. So what is the result of the filtering here? I get a feature map. Answer is see, put output of each stage. I get a feature map. I get a feature map. I get a feature map. Then I do max pooling. What does max pooling? It is the same feature map, but it is reduced. It is reduced. Reduced feature map. F. I'll write feature, then I'll write map. And this now you can do it many times. So when we go to the actual CNNs, I'll show you convolution max pooling, convolution max pooling, convolution max pooling. You can, people are using 10 times, 20 times, 30 times. We will come to that how many times to use, how they achieve. But first we are understanding simple things. So I take an image. When I do training, I do convolution with the help of filters. Then I do max pooling. I repeat it many times. So now this problem can be anything. Here I have taken example of cat. Here I have taken example of cat. So what was traditional machine learning doing? It was taking some eyes. So cat's eyes is like this. So I'll go and take out. So it was handcrafting features. It is looking at the problem and saying that, okay, this is a cat example, cat dog problem. Now I'll go and see its eyes. Now I'll go and see its mustache. Right? That is how traditional machine learning was being done, was feature extraction was doing, which I have explained in my earlier yesterday evening's class. Okay, with some examples I have. Now I don't bother. Let us close our eyes. Right? Generally, cat closes eyes and drinks milk. That's a different matter. Okay, let's close our eyes and say this. Suppose this is not cat. Suppose this is 0. Digit 0. Suppose this is 1, digit 1. Suppose this is digit 2. We are handwritten. We are doing handwritten recognition. There also you have to do convolution and max pooling. You don't need to understand what problem you are trying to solve. Just pick up the filter. Yes, filter choice is little bit technical. We'll go to that, but it is simpler as compared to studying the problem. So what happens? So any mechanical person won't understand image processing. They will say, I cannot do it for handcrafting. But here, any person across, so nowadays you are seeing even in commerce, they are doing this CNN to predict Reliance Industries or Tata shares. They are using CNNs. They don't know anything what is CNN. They don't know. For them, it's a black box. But we are machine learning scientists or researchers. We should know what is convolution. Sir, what is machine learning? I am not able to do anything inside, only it does. I am not able to tune. But it's not like that. You can tune, you can understand what is convolution, you can understand max learning, the max pooling. So what we get out of each stage. So I'll just reduce this because it looks very bad. I have annotated it because this is my habit in my regular classes also. I try to annotate as far as possible, okay, to make people understand. But after that, sometimes when I see it becomes very bad. Okay, so here it's looking bad, so I just remove this, right? I bring by my annotation here. Okay, so let's go back here. What I'm trying to say, I'll change the in color so I can make it so let me use this green, right? So what I'm trying to say is, what is the result of these two stage? This result of these two stage is a new image because I have taken cat. It might be anything. So here we get reduced number of people, reduced feature set. I can repeat this many times. So when I repeat this, I get smaller than the original image. Okay, the number of channels in the is also the reduced. So here I go on reducing this. So right. So I go on doing this convolution, max pooling, convolution, max pooling, convolution. Some place I have to stop. Some place I have to stop. That process where I have to stop is called flattening. So after repeating convolution, max pooling, convolution, max pooling, convolution, max pooling, then I have to flatten. Flatten means whatever you wrote in this direction, like this, whatever you wrote. I wrote here 1, 2, 3, 4, 8 people, right? 8 people I wrote like this, one top of the other. I should write it serially. So what I do, I write this first here. This was 3. Same example I have taken. So you could do this. This and next I put it here. This is called flattening. So I put this person here. Next I take this -1. I flatten this. I put it here. This one comes here. And finally this one comes here. This one comes. Simple example I have taken. See, these are all neural network. They are very well connected. I have just taken simple examples, right? So I'll just remove my annotation because again, as usual, it looks bad, right? So why I'm trying to say is, please take some interest here and understand. Don't remember that as convolution, max pooling, flattening. Why it is done, you should understand. So if you understand, then nobody can take away the concepts from you. So what I have done, I have flattened. So I have flattened now. See, this is how it is flattened. So whatever garbage connection I did like this now is shown here. So this is nothing but fully connected feed forward network. Fully connected full feed forward network, and this will give you the classification. So now I take this with the this is the cat, this is the cat. It's a convolution. So I bring back my pen. So let me bring back my pen. So here, this is the cat which is coming in. This is a training I'm doing. Training, I'm doing convolution, max pooling, one stage. Again, I repeat, I have taken here example only 2 stages. Typically, you have 7, 8, 10, 12 like that. After doing this, I flatten. Flatten means just connecting it this. Then this network will be able to tell me what is a cat, what is a dog. So my question is, how will it be able to tell? How will it be able to tell it is a cat or a dog? The reason is, these numbers will be different for a cat. The feature representation will be different for a cat. These numbers will be different for a dog. And the neural network will learn and build its own boundary. Internally, it will build these numbers. It will see these features. This is very intelligent neural network. You have to do training, right? It will itself. So these numbers are special. Feature maps for dogs will be different. For different category of dogs will be different. Feature maps for cats will be different. For different categories of cat will be different. But you have the label with you. You are doing supervised classification. You have the label. You are going to tell that these are the 1,000 cats. These are the types of cat, and every label is cat, cat, cat. So then you are telling these are 1,000 dogs, right? These are the these are 10 variety of dogs, German Shepherd, Pomeranian, etc. And these are the label for dog. So you are trying to say this. Okay, so what we are here, these numbers are going to be different, and your CNN will output cat and dog properly, right? And all these are one line functions in TensorFlow or PyTorch. When we are going to do today, we'll see they are nothing but one line functions. Please note, one line function. Though I have taken an hour, I just saw my time, it's an hour that I am speaking here on this problem, but for doing it just 10 minutes, 5-10 minutes, just reuse all your from your libraries, do it, it will give you the answer. Okay, so here let's do this, right? So let's try to see how it works. So input, so I am taken an example of Kiras. So I have taken some numbers. Let us take an image of size 28, 28, 1. So your cat, no, go to previous image. This size of the cat is simple. I take 28, 28. Just for namesake here, because we cannot train 1204, 1024. The size is 28 cross 28. Now we have to go to do this. So my image is, see, this is the image size 28, 28, 1 that I will show you in my notebook. Convolution, 3 cross 3 mask, 3 cross 3, 2D convolution I'll do, right? So this is 25 filters I use, 25 filter, assume. So 1, 2 filters I have shown you. I am using 25 filters, right? Of size 3 by 3. When I do this, right? There are 25 3 cross 3 filters, whatever 2 I have shown. It took me so much time, assume now 25. So you see how much time it will take for doing the training. So I do this, I go ahead. So input shape is 28 cross 28 cross 1. So I got 28 cross 28 pixels. So 1 means it is whatever example I have taken here is a black and white image, gray level image. And if I put 3, so 28 cross 28 cross 3, it's an RGB image. So number of computations will increase. So number of computations will increase. Max pooling. So see, this is the model 2 max pooling 2D direct function, right? Pooling, max pooling 2. Just give the parameters. So it will just the same example here, max pooling for 2 by 2. The mask is 2 by 2. So 4, it will going to do it via 4. So here you get 3, right? So now let us go ahead and do this problem. I take my input, I do convolution, right? I got 25 cross 26 cross this. So I do max pooling 2 by 2. So my size becomes less. My size becomes less. Again, I do convolution. So here I do, like, this is my size. Again, I do max pooling. I go on getting, so how many parameters? So write the parameters, right? Go on writing parameters. So this is what is called hyperparameters. So you would have referred in books hyperparameter. So you don't need to get hypertension for that. Very simple it is. Multiply all the values, multiply your values, 9 because 3 by 3 mask. Then you go on multiplying step by step. Then you are going on getting your hyperparameters. But for real images, simple example I have taken here. For real images, your hyperparameters are lakhs, many lakhs, nearing millions. So for real images. So let's do this. I have brought the same thing from here to here. I'll do this. I'll flatten this. When I flatten this, I get 1250 parameters. I will connect it and I will get my output. Okay. So step by step, I am showing here for you from input when we started, that did all your steps along with my hyperparameters. I go here, I go on top, and here I got my output. So how do I see? So this is what are the functions that are required. I'll show it in my notebook also. These are my functions that I have used. So you can use some, I'll tell you about softmax and all a little bit later. An activation function, non-linearity a little bit later. But now you can think that you should know convolution, you should know max pooling, that this is repeated, then you should know flattening. And then you should know that is what is the general structure of a CNN. That much is sufficient for now. So let us take this example here. Okay, so I think we'll go with this. Yeah. So how is this, whatever we learned now, different from what we did earlier? So what was classical computer vision, which happened around 2000 to 2009? Extract features. Yesterday only we have seen some texture features, So I think people who have done imaging, you know what is surf. These are all features, some features. All these are handcrafted features. They are features. So this is how traditional machine learning was being done. This is how your features were being learned. Shift, soft, surf, hog, rift, all of this. So you did feature extraction, took an image, did feature extraction, you extracted features, then you gave it to a classifier to training. Then you gave it to a classifier learned it, then it said there is a dog, there is a child, there is a ball, there is something else here, etc., etc. So this was machine learning for traditional machine learning, which is called classical machine learning in computer vision community, with images, with videos and all that stuff. But now the thing is changed. Why it has changed? Here classical computer vision is domain specific and time consuming. Somebody doesn't know about surf. Many of you may not know about this. Those who have done imaging only know about this. So does it mean you cannot do computer vision machine learning? Answer is no, you can do with the help of deep learning. So how do we deep learning does? Deep learning takes this, build feature automatically. You don't need to give any feature. Only what you have to do, convolution. So what is deep neural network? It is combination of convolution neural network, CNN, what we did. Then you are having max pooling. So this is what max pooling. Then you are going to repeat this max pooling or average pooling. So it is not necessary that every time I will write max. I can also say average pooling. Average pooling. So then I go on repeating this average pool. I go on repeating this stage, 10 stage, 20 stage. Here where it becomes deep. See how you go to our real life. You go to real life and say what is deep. So you only say that this pit is deep, right? This pit is not deep. This well, whatever has been dug is very deep well. This river is very deep. Don't go to swimming there. You're referring this, no? It means the depth is very large. So if you do convolution, this max pooling, convolution, average pool 40 times, 40, 50, 40 times, 50 times if you do this, then you are doing what? Then you are going deep. Then it is deep neural network, right? It's a deep neural net. Opposite to deep, our common example, shallow. So our common, I'm writing here, shallow. Shallow means it is not deep. So what is a shallow network? The number of CNN and max pooling and all these layers are less. 5, 6, 3, 8 like that, not many. So deep neural network means it is very deep. You have lot of these neural networks hidden. So what does every layer do? Every layer does a feature representation. Every we did filter into mass computing without domain knowledge. So this is what I say, build features without knowing the any of the domain automatically based on training data, right? Then you do this, it will also classify this, right? Combine. So what is happening here is, so you see here, what is happening here is your deep learning is going to combine feature extraction and classification. You don't need to say, you don't need to build separate feature extractor, classifier, both are together, right? So here let us go to cat and dog problem here. This is how it works on a multi-layer. I take this example. Okay, this is a cat input, right? This is, see, I'm just marking whatever I have shown on top is my output, and whatever is shown here is the input, and whatever I am showing here in between are CNN layers, hidden. They are all hidden. CNN. If I say CNN, it's understood. Max pooling is there, flattening is there. All those things are, it's understood. They come together. So whatever are shown here. So let's see. So I going on giving cats. I go on giving dogs, right? I train. I go on training. What is the training algorithm that I can use? Anybody? Yesterday's class we have learned. Can you type on the chat box? Yesterday we have done it. Yes, as Naveen said, one of the participants is telling, Naveen is telling back propagation, use back propagation, train it. Go on training, do this. So every time training, it will see what is back propagation. Yesterday I have shown in my GIF all the vectors. If the target is wrong, it will correct, it will come back, and it will, the mean square error should be reduced. Go on reducing mean square error, finish the training. So we train, and we finish our training here, and we come to our problem, right? And now our network is trained. So our network is now ready. So once our network is ready to give the classification, go and test it. Give it a cat. So when you give it a cat, only those neurons belonging to cat will fire. So all those people will be active. It will see the input image. It will say, this belongs to me. This is my weight. He is mine. Like this input example is mine. So whatever are shown in yellow belongs to the cat. Belongs to the cat. They have, these neurons learned what is the cat. And whatever is in the other color are the neurons who have learned for a dog. So what happens? Okay, that will be cat. Now when you give it a dog, a new sample which you have not used during training, if you give, the neurons belonging to dog will fire. So these are the neurons which will fire, and it will cat, and it will say a dog. Okay, so what we are trying to understand in the basic sense is, once your network is trained using CNNs without your domain knowledge in deep learning, how many such CNNs are there? Maybe 30, depends on your problem. Maybe 30, maybe 40, 80, 90, 100, I don't know. Okay, it all depends. I'm going to take example what Google did, what IBM does, what your GE does. Examples I will take later, but what I'm trying to say, deep network it is. So once that is trained, only those neurons belonging to that proper class will fire, and it will tell cat. It will say a dog. Okay, so what is a convolution neural network? If I want to summarize, I'm almost coming to the end of this particular part, then we'll go to the collab notebooks. What is convolution neural? It's a multi-layer neural network architecture. Please understand, in CNN, there is no SVM. Okay, there is no decision tree. CNN means only neural network, hidden network it is. It is trained via this backpropagation algorithm, and how it is representing features, dot product, over. If you know this much, you know everything, right? So this is how it is. So let's take here input layer, feature map. So all of us know now what is this. So convolution layer, subsampling layer is called pooling. Subsampling layer is pooling. So you get reduced feature map. Again, so you can then you fully connect, then you are going to get a output, right? So convolution layer plus non-linear layer, it is subsampling is there. All of these together fire, all of these together fire depending on the class. So it is a supervised learner. It's a supervised learner. Okay, so this is what is a convolution neural network. I hope I'm clear with this. So see what I have tried to do. I have tried to build this. See these with two colors. Whatever I have built with the white color is nothing but my feature extraction. Traditional feature extraction is here. So let me go here. So this is whatever CNN, whatever is here is called feature extraction. So it is feature extraction. How it is done? Using CNN and maxpool. And this part, whatever is done here, is classification using flattening. So both are together they work. You cannot say I will use separately. So if you use CNN and all this feature map and all this connection, they come together as a box. So you have to use feature extraction and classification together. So that is how it is. Okay, so here convolution neural network, it is just an extension of your multi-layer perceptron. Yesterday I have told you about the perceptron. What it does, it is local, because we did it locally, going on sliding. It is sharing the weight like representation. Then we are going to subsample, seeing this particular part. And whatever I have told is not, though deep learning came in 2012, afterwards 2014, I'll come to that, but it was first investigated by Lucan. I think currently Lucan is with the Google group in 1998 with this particular paper. So you can go to this paper and learn about this. This is for used for text recognition. So he gave images of 0, 1, 2, 3, 4, 5, like till 9, which we call a traditional handwritten data set. And he trained it and told that why you people, he told the community, when I'm saying the community, machine learning community, he told, why you are using feature extraction separately and classification separately and doing domain specific knowledge, why you are doing this, right? Let us use it together using something called, what I have found out, convolution neural network, and let us use this. Though this paper was published, nobody gave importance to him, because all of the community was saying that feature extraction, handcrafted feature extraction, then classification using some SVM or some other neural network. What he was trying to say, let us combine both and do this. Why don't you believe? So he was never given importance, but he continued his work just like Fourier. I hope people here know about Fourier. Fourier transform was rejected thrice. His paper was rejected thrice. Nobody accepted Fourier transform. Simple reason, I'm just deviating out of the topic. Simple reason, because he did not have, Fourier was an engineer, right? And whoever were reviewing him were mathematicians. They were asking him how you can prove that sum of sines and cosines, any signal can be built with sum of sines and cosines. They were asking him. What he was trying to say, see, we can work out, you take any rectangular function, you can write as sum as far, and showed the proof. They said, prove it, right? They were saying that no, we cannot accept. He said, I cannot prove, I can only show that this is what is working. He was an engineer from engineering point of view. So who was evaluating him was Lagrange, all these people who were mathematicians. They were saying, where are the conditions where it does not work, you show. He was saying, I don't know. So for 20-25 years nobody accepted him, and after his paper was accepted, after that he passed away. Nowadays, till now, Fourier transform is used. And who gave a simplistic example is Dirichlet. When Dirichlet came and gave the limiting condition that signal should have discontinuities, like you should be finite, all that things when he gave, then people believed, oh yeah, Fourier transform works. Same thing is with machine learning. Lee Kun in 1998, please see, 1998 paper it is, was telling that there is something called convolution neural network. Nobody believed, because people go behind show. People don't go behind the actual knowledge. They go behind show. Whatever is like big show, they will go there, right? So people are thinking, no, I'm going to do machine learning via this traditional. So he was trying to sell same traditional, I'm extending, but they were not believing. So but Lee Kun now is a very big person. So it recognition came to him, but came late. So but he published this, so I can ask the participants to go through this paper where Lee Kun has told. So basically, what is a convolution network? If I want to say it's a neural network which does this, simple example I am giving, right? Which I give in all my slides. So I go back, I do it again. This is what it does. So who is moving here? Filter. And it represents one person. Like this, you go on doing next, go on doing like this, right? You get then subsample, you get a feature map, subsample. Again subsample, this is max pooling, go like this, go ahead, right? And finally you go and get into your results. So this is how, what is a convolution neural network, how it started. So I'm just coming to this. You should know, people were using this handcrafted till 2012, but in 2012 what happened was, there was a challenge. It was called Image Large Scale Visual Recognition Challenge, ILSVRC. So in this challenge, see this 14 million images were given, right? And 20,000 classes are there. Please see what I am trying to say, right? I am trying to say that I am telling you cat and dog, door and window, right? Shirt, checkered, non-checkered, right? 0, 1, 2, 3, 9 classes, A, B, C, D, 26 classes, 20,000 classes, 20,000. How many images? 14 million. Do the training. They said train it. Go ahead. People tried doing what? People tried handcrafting, all that. You saw the images. This is dog. You do this handcrafting, texture, shift, use that. Everything believed. Nobody worked. Right? Training time took 10 days, 18 days, 3 months, 4 months. Challenge is challenge. It has to be broken. And it was here, right? Here, this challenge was broken here by a deep learner, where convolution neural network was used and told you go on training. So in these 20,000 labels, few of the labels I am showing it here. Okay, few of the labels I am showing it here. What is this? Lens cap, abacus, slug, hen, planetarium, all this tiger. Okay, and these were the labeled. Some examples I have taken from that classification challenge. So, but there may be a second. This might be a cat also, big cat. But tiger a cat belong to the same family, right? So the first classification is tiger. Next, it can also be a cat, right? Who won the challenge? ImageNet challenge, ImageNet data challenge was won by a CNN. All other people failed. All other people failed on this data set. Then who was remembered? You know, Lee Kun was remembered. And he was telling here in 2012, he was telling in 1998 same thing. So in we call in Hindi Vidambana. So this is the Vidambana. Somebody speaks the truth, right? He or she is put at the no go from here, right? But recognition comes in 2012. So a person who said for text digits it works got recognition via ImageNet. Then everybody started remembering Kuliko. It's very funny, right? It's very funny, but it's a fact. I'm not joking here, right? We are in a traditional GIAN setup. This is what happened, and machine learning community said, now let us go to deep learning. So see how it changes overnight. So from one to here, it took almost 14 years for the recognition to Likun, right? On this challenge here. Now you give a scene, it will tell. Nowadays, I'll show you many examples. Right now, you see this is 2013 Tarblet paper. Here, it will tell this is sky, this is road, this is cycle, this is car. Everything it will tell because convolution neural network is so strong, right? So it can tell internal things also. It can tell it is window, chair, dog. If there is a dog, etc. Just go on giving it labels. Train the CNN, it will tell everything. Okay, so here I'm just going through because we are fast, a little bit fast, and not only on images, it works on action data set also. So somebody may jump, somebody may skip, somebody may say like this, all actions can be recognized. So that was done in 2010, right? So there is a lot of this word on this deep learning here. So it is even used in speech processing. So if there are any participants who are in speech, here also it is there in optical character recognition. Then I think Alexa, the assistant what we use, Google Assistant what we use, all are deep learners. So even if you are getting Baidu is also one more visual search. I'll give you a few more examples when we go, right? So now everybody left all the handcrafting, and now everybody have gone into deep learning. So where we see a lot of promise, and all major companies, Google. So you can see you email you anybody down, it gives you suggestion. I'll come to that a little bit later. So it says some email is there that I want to do, then yes, thank you. All these things are Google has already read it, right? So this is a lot of buzz about deep learning here. So Google is doing this, a lot of things, all your mails are being read by Google, right? So, and they have set up a separate search team, etc. for this. And I think this ImageNet example, they have solved this challenge goes ISL VRC challenge goes every year. Current winner is Google group. So they call it Google Brain. So that's why it is called here. The group here is Google Brain. So you could see these researchers in the Google Brain group. So these are the people who are working on all our things. So Google Brain, like that, we have Apple. So we have your GE, all these people. So a lot of investment has gone into this. So here Facebook also uses all this intelligence. So Lee Kun, whoever was told that your 1998 paper is not valid, is now heading. I think he also left Facebook. So he is heading the Facebook's AI group. So he is a faculty earlier with the university. Now I think now again he changed. Now he is with Google, right? So here he is now leading in from 1998 till this day. He is leading the group. So same Lee Kun, right? So it is the same person here, Lee Kun here, right? So Lee Kun here in between here, who was the person who proposed this, and now he is heading the Facebook's new AI group from 2013. He was a New York University professor who was the founder of deep learning, right? So with this, I think I am ending it here with regard to my formal presentation, so that we devote an hour's time for the notebooks, whatever my students have prepared. So we'll devote some time to that, and I'll just discard the annotation. Before that, I'll take a 2 minute to ask you if you have any. I'll stop sharing. Yeah, I'll stop my share and ask you if you have any things with regard to asking me any questions. So I'm open. So I'm seeing my chat box. So please, if you have any issues or you want to understand anything else, you are not feeling comfortable to talk on this, so you please ask me. I'll be happy to answer you. I don't require a break, of course. I can go till 1 easily, but for this session I reserved it till 12. So I don't require a break at all. So is it okay? Should we start with our notebooks? Have you understood? Broadly, see, I would have told 100%. It's not necessary you would have got all 100%. So let us give you a benefit of doubt. Even if you have understood 70 to 75%, it is still fair enough. So it is worth the time that you have spent for the last 2 hours with me. Is it okay? So can I get a confirmation in chat that is it okay? Okay, so I get one confirmation, so that means that I go ahead. So now what is my plan? So again, collab notebooks we start. So I'll put my share screen again on. So I am sharing my entire screen as usual. So I share my sound as well as optimize the video clip. So let's go quickly with regard to this. So this is over. So we go back to our collab session. So before we go to CNN, yesterday's part, we'll do this. For ensemble methods, I do. Quickly, I'll tell you what this is. Ensemble methods. So yesterday we have done non-ensemble methods, though I did not tell you it is non-ensemble. So let us go and do ensemble. So let's quickly go through yesterday's part, what we have done. So what was our task? Quickly, I'll go because we have to have connectivity. If we do not have connectivity, then we will not understand. So let us take what we have done. We have taken a simple iris data set. So I'll bring back my pointer here. Yeah. So I bring back my pointer. So I have taken a simple iris data set. So as I know, I have 150 samples of iris data set, 150 samples of flowers. And what are the features? Petal features and sepal features are my features. So petal width and length, and sepal width and length. So data set is iris flowers. And these are the three classes: versicolor, setosa, and this virginica. So these are the three examples that we took yesterday. We saw that these are the features. So these are the features here, and this is the target. This is the target because I cannot give names. 0 means setosa, 1 means versicolor, so 1 means, and 2 means virginica. So these are the things that we have done yesterday, and we have split it. How we have done? These features are fed to the classifier by doing what? This ratio: 80% training. So 80 thumb rule. So 80% train. So this is the train, and 20% test. This is train and 20% test. So 20% test. We have done this yesterday collab notebook. So this is what we did, and we plotted some. So 3 classifiers we did. This is how we split the data, and 3 classifiers we did. Decision tree we did yesterday evening. We did logistic regression, and we did SVM classifier. Right. Today we are going to do. We are going to go ahead with the next ensemble methods. So now I want to give you an analogy here. So what happens, this I think yesterday also many people may have this question or may or not have asked this to me yesterday. General thing is, whenever you have this classification, one general question whenever I go for any talk, I get this question that, sir, how you will decide which classifier to use? I think this question is for you also coming to your head, that how one decides what is the classifier that you use, right? So obviously one answer is very easy. From today's lecture, I think from morning class, you can understand one thing is very easy. What is that? If I have for million, 100 million images and I have 20,000 categories, what is the classifier that you'll use? Anybody can tell this? It should be easy by putting in a chat box. What is the classifier that you will use? 20,000 categories, millions of images. Which classifier you will use? Yes, I got the answer. Say the CNN. Obviously, you will use CNN, right? But now it is not that very simple that okay, every time CNNs will be useful. Sometimes CNNs may not be useful. Machine learning itself is very challenging. Every day, some or the other invention is made. There is a thing that we have SVM. So I'm writing it here. We have SVM. We have our neural network. I'm just writing NN, neural network. We have logistic regression. We have what our next, whatever we learned, what is that? Decision tree. We have some random forest, naive Bayes. So all these naive Bayes are there. Which to use? Naive Bayes. All these classifiers are there. Which to use? One of the answers is what we did yesterday. Go on using one by one. See which is good. Whatever is the task, use it. Fair enough. Nothing wrong in this, right? But now once you get something, you want to get something more. That is what is human tendency. So now the task is, can we use all of this on the same problem together and then decide which is working good, or take the collection of this, give all the data to these people, then you just do some sort of a selection, whatever all see. It is like making a committee. So somebody made, I give a simple example. Somebody made a committee here to look into some a committee is formed to choose the best flower vendor in your city. So what is going to happen? 6 people are going to go to different shops, find out here which is the best flower vendor. So it is more likely that, right, all of these 6 people, this is a committee which is there. So out of these 6 people, say 4 people will recommend one flower vendor, right? And one person may recommend one, and one more person may recommend one vendor, right? So what we are going to do? So here in this case, these 4 people, there are 2 ways in which you can do this. These 4 people will go and visit these 2 people, these 2 vendors, and these 2 people will go and visit this vendor who these 4 people have selected, and they will converge and say this whatever is the majority, and they will say that here whatever is majority is correct. Suppose the committee is independent, unbiased majority. So the majority prevails here. So out of 6 people, whoever, if 5 people or 4 people told correct, then we are going to go with that. This is called ensemble. Ensemble helps. So it is helping in doing some job of classification by using many machine learning algorithms. So let's go here, take the same example, classification of simple iris data set. So again, it's a 3-class problem, Setosa, Virginica, and versicolor, right? Flower data set is same, 150 samples. Features are petal width and all that, whatever I've explained. Let us go and see what is an ensemble classifier. So whatever I told example here, it's on my slide. It combines several base models. It can be replaced with the word model. Many people in machine learning say they don't say classifier, they say model. So this is your model, that is your model, this is what they say. Okay. So what is the goal of the ensemble method is to predict, right? I think there is some. So can you put your mic in mute, please? So can you put this in the mic? So I'm sorry for this. The administrator, can you put him on this? Yeah. So I think here the goal of ensemble methods is to combine the predictions of several base estimators, right, in order to improve generalizability. So this is what is the goal, right? So we want to be better predictor. By instead of using a single estimator, yesterday we used single estimator, now we are going to use ensemble. So what is this ensemble? Several examples are there. One of the example is called bagging. So you will read this in machine learning literature. Bagging means it is like a parallel. Let one data set, that entire data set is split, and the classifier is run on that. It will give one decision. Again on the next subsampled one more classifier is run, different classifier. One more here, it is split, one more classifier is run. Then whatever is the outputs of all this, take an average of this. So this concept, if you are doing in parallel, it is called bagging, right? And if you do the same job in sequential, you take the data set. So same iris data set I split of 150, that 120 I split it into 3 groups. On one group I will run one classifier, that output I'll give here, then again I give it to next classifier, then I come in, give it here, then again I come here, then I average it out, then I see which is the best result. Then that is called boosting. It improves. So here this bagging and boosting are two types, and one more is voting. Here I have a decision tree, it says it is class A. Here it is a decision tree, right? Here it says class A. Here it is decision tree, it says it's class B for the same data set. Suppose on this data set, so two people are telling, so we go for a majority, which is called voting. So all these three decisions are seen from the three decision trees, and majority is taken and it is voting. And all these voting, etc., are again one line commands in our notebook, what we see, right? So let's go here. Let us go here with this. I'll discard this. Go to our notebook, right? So I am going to my notebook of ensemble methods. So again, as I told today, I'm just reducing the slide. I told today that this also will not take much time. It will run. But when I go to CNNs, that will take time. So let us go to the ensemble notebooks. So this is again shareable. So I've told you this. Again, I'm telling for those people who couldn't join yesterday, all our Python notebooks, interactive Python notebooks will be shared together once the course is over. Because if I share it now, there may be some modification which may happen. So I'm not sharing it now. So here ensemble methods. So here these are the three things: bagging, boosting, and voting. So this is the same thing which this I think has been done by my student Ayush. So Ayush has done this notebook here. So this is bagging this. So you can see notebook is so nice that you can also copy a image here. From here only I have say copy image and I have pasted on my slide, right? So that's how it's been done. So Ayush has done this. So it's parallel sequential. See, we take the necessary imports, right? This is very important. NumPy, Pandas, Matplotlib, and you are going to take any other data sets like this. So if there are any imports, do import. Okay, say run. It takes some time. Yeah, I get a tick mark here, means this cell has run. Come down. My next job would be to get the iris data set. And we have known from our yesterday's class that it is sklearn. So take the data set and load it. I can increase the font if you are facing difficulty in seeing. So you see data is loaded, right? You can show it. So with the feature names, I'm creating a data frame where adding the target value, and I just I'm seeing the 5 rows. Yesterday also I've shown you 5 rows, right? So these are petal width, sepal width, petal length, etc. Species is 0, means it belongs to the 0th class. So you may have there are 150 examples. So you can just do this. You can also calculate this. You can describe this, right? Species and all this stuff. Let's go to the information. How many values are there? We want to know the information. So there are these. You see this 150 means that so many examples are samples are there. Petal length, petal width, sepal length, sepal width. species, you have these many, right? So this is how you are going to have your data. And now you can visualize this. So I can visualize this. So this command dot plot is from matplotlib. So you see matplotlib, I am executing this scatter matrix. So I am plotting one by one. I plotted sepal width versus sepal length. When I say I, the notebook. Okay, so the notebook is plotting. This is a scatter plot. Earlier days when we were writing machine learning, we were writing big amount of codes to plot a scatter plot. Now it is very simple. It is available in matplotlib. You take the dataset iris, say a plot. What kind of plot you want? It's a scatter. What are the features you want to plot? Sepal length, sepal width, x and y axis. Do that and you see this is how it is, right? You want to show there are different kind of plots. So there is one more facet plot also. It looks a little bit different, colorful. So if you want to plot that, same thing you can see for 3 colors, for 3 species, iris, setosa, virginica, and that 3 species, whatever you have, we have named it. So this is plain here. You won't understand, but it is the same. But if I want to give it in a different, better interactive colors, I can see 3 different colors here: blue, yellow, and green. And here you can see boundary building is easy for this. So you can build a boundary easily here. Between blue and rest, it is easy. But rest of the 2 people, this orange and green, little bit difficult. That is why you saw decision tree yesterday, what it was trying to do, it split next. If you can remember yesterday's part. So I have it here. So I just show it because we should have continuity. So let's go here. So see this iris example, whatever we did yesterday. See, this decision rule was easy for one. Whatever is being shown, that blue color was easy. But here there was a mix up of 2 classes were very close enough. So what decision tree did, it did not take a decision here. It used one more feature to break the tie, and here it went and then it classified between that orange and the other color. So the same example here is being shown in my notebook. This green and orange is being split by the decision tree next. So here one is easy. So this blue one is very easy. 0th class is very easy. The first class is little bit difficult with the second class, right? So that's why decision tree did this. Then you can also show the distance. So here in a box plot, just like scatter plot, you have a box plot. So this is the box plot. Here also you see the distance between this blue and this is very large. So your boundary is very easily here that you can draw a boundary here. But these 2 people are a little bit close enough. So you should draw boundary properly, right? So this is how we get this. So let us plot each of the figures. So here we are plotting each of these figures. I'm not going into very large detail of this. I am here, what I'm trying to say, we have different properties, sepal length, sepal width, all that. So here I am plotting everything. Sepal length here versus the category, the y-axis is, sorry, the x-axis is category. There are 3 categories, 0, 1, 2. So sepal length you plot, you see where they are. Sepal width you plot, you see where they are, right? Then you see petal length where they are, petal width where they are, like this. And then you can combine 2, 3 together. That what you saw the scatter matrix. So you could plot this. So here this is how it plots. You can show this. Now come to the creating feature and label values. So we are coming again, train test. We did yesterday 80-20. Here split is 20%. See, test size is 0.2. 20% is given here. Same we have kept. So I am just splitting this data into train and test. Now our job is to go with the classifier. Right now our job is to go with the classifier. So here let us go with the random forest. So let us, I think we have not learned random forest. Random forest is nothing but a number of decision trees together. So this is ensemble we are doing now. So what we are going to do, we are going to use several decision trees, not one decision tree. So here red color, you see there is one decision tree. Next you are having blue color, then this color, yellow color, several predictions you are going to have. Then you are going to take like this. You are like a vote, right? So what we do, it's a random. For this I think I have shown on my slide, example and voting. So I go here and do using random forest classifier to train and test the data. So you see random forest classifier is directly available I only need to word ensemble. When I use ensemble, it means several decision trees are going to come together along with a random classifier, random forest classifier, come together, work, find out a common label and give the result. And entropy, it is going to use entropy. Yesterday Professor Barni was using this term entropy, right? So we are also seeing here the entropy is used. Again, it comes from mathematics, that is the loss function. Then again you see here train test. So you are doing training here, so you are doing X train, Y train, right? So this is how you do. So I run this to train and fit the data. Now let us predict. Classifier is built to predict the labels. So let us predict it. So why forest prediction? The test data I am giving. So you should not give test data. And so let's see how it looks. So real data was at 73 flowers. There are 150 flower samples. 73rd sample was belonging to category 1. You check what it is, Sentosa or versicolor, whatever. The classifier predicted as 1, correct. It was 0, right? Real was 0. So prediction was, so you can draw a confusion matrix here. So there is no misclassification here for these 5 samples. So you could just do this, and after this you can evaluate the confusion matrix for the entire part. So you can evaluate the confusion matrix. So one of the confusion matrix here, I have shown yesterday's class. I think I have it in my confusion matrix lecture here. So just go quickly to my confusion matrix because it's very important, because we should link our theory with the code. So I'm just importing this part here. So let's quickly come to the confusion matrix part, what we have done. Here, let us see. Yeah. So please see here, I'm just putting it in full screen for you. So you see here, these are the tests. I'm putting a pointer again. This is what is your test where you know this actual values. This is test. Whatever test sample you are using, you know, na? And you want to see whether you are predicting it correctly or not. You want to see its prediction, right? So it is just like you are making your son or daughter write something. So you are testing. So what you are saying, you write A. You are going to see whether that person writes A or whether that person writes some other. So accordingly, you're going to say whether your prediction, whether your teaching is correct or not. So here, one of the values to the confusion matrix is actual value, and one more is your prediction, whatever your random forest. In our example, this example, random forest. So let us go here. So I'll discard this. Let us come here to our notebook. See here, accuracy here, test, you know this, and you want to find what is the prediction, PRET. So confusion matrix is one line command, as I told. Put your test samples and you see what is your random forest going to predict. So once you do this, right, so this has run, you want to display it. So you let us display this. So here it is being displayed. See, it is 100% correct. Yesterday's was 96.6. Please recall, by using individual decision tree, we got 96.6. But when we combined several decision trees and got a random forest, we got 100%. Accuracy is 1. Though this is not very correct because I am taking a very small data set. This is because to explain you in real life, many complex things are there. It trains hours, it takes in training. I'm taking a simple, so you got 100% accuracy. Please understand that you won't get 100% accuracy because the data set is small, you got 100%. So here, let's do this. So here, this is how it is printed. So this is your random forest classification using voting based approach. This is what is your random forest classifier. Next, coming to AdaBoost, the boosting, what is there? So you take your data set D1, right? Original data set, try to make a model with this, iterate on this, do some prediction, boosting. It is going to be sequential. Do some boosting on this, right? Here we are doing boosting. So here I think there is some disturbance. Again, there is some mute. Please mute your mic. Yeah. So AdaBoost, you say boosting we're trying to do, it's an ensemble. So why use ensemble? Because we are going to get better classification than earlier. So we use ensemble boosting. Here we used ensemble boosting. So what we do, boosting we have learned earlier on our slide. We take a data set, split it into model iteration, do some prediction, update the weight, give it on dataset D2. Then again use the next model here, predict, again give sequential here. Again do this. You can go on doing this for many times. So this is how it is. Model 1, weight 1, model 2, it is going to give weight 2. We are again feeding this. It is going sequential. So it is just like an example. Many weak people, you can give you this example, many weak classifiers when combined together give a strong classifier. So this is the thing of boosting. So what we are trying to do, weak models and get a stronger model. So we are going to get this enable with all its predecessors. So let's use this. You see ensemble, right? Import ADA boost classifier. So it is automatically going to use the boosting. So everything is written in sklearn, which is a library of TensorFlow. So you are going to get this. So we are going to take this, we are run this. So it's giving you it as run. Let us come down. Let us predict the result and see how the prediction looks. So this is predict, why predict? So this is the command for that. On our test set, let's see the first 5 rows, how it has predicted. So here again 73 is, I think still there is some mute issue. Have to mute. Yeah. So here I am just predicting here. So you look, let us evaluate this. Let's evaluate the performance. So how do we evaluate the performance? Confusion matrix and accuracy score. So here again confusion matrix is plot. Again you get accuracy of 1. So yesterday we have seen if you use normal things, you are going to get 96. But by doing this, you are going to get better boosting. So like ADA boost, there is something called gradient. We won't go much into this because of lack of time. Lot of boosting methods are there, but ADA boost and are the more frequently used. So you can do this like this also. Ensemble prediction. I'll just not go into this. I'll run it, however, for your understanding. So grading, this is also a boosting method. Predict this. Why predict GRAD gradient? Because I have used why predict earlier. So it will override that. So we have used gradient here to tell this is our own defined variable. So gradient classifier is already available. Use it and predict it. You see how your prediction values come. So you get this on the test set and you can just see how it goes again for the 5 rows. Again, the prediction is all correct. Let us evaluate that on the model, right? So let us see this classification here is again going to be 1. So here both the boosting methods, the ADA boost as well as gradient, is which to use. Again, it depends. You are a machine learning engineer, so you should decide based on your problem. So finally, quickly, we are going through voting. Voting classifier is very important. It's used everywhere. So I'm going to my slide here. So here I'm just going to my slide to tell you an example of voting classifier. So let's go here. This is where we had stopped. So this is very important. What is a voting? So voting means it's majority, right? So it is the same committee example which went to pick flower vendor example here. You have a problem at hand. So here you have a problem at hand. So here you have a problem at hand, any problem it may be. And what you're trying to do, you're going to use several people. Logistic regressor, yesterday we have seen, SVM we have seen, naive Bayes I have no time to tell, but you can assume it's a classifier which does using Bayes theorem. Decision tree we have seen, any other is there. Use all these different models. When I say models, these are all classifiers, they are referred as models. And let's see what is the class prediction that they do. So for some instance, it is saying that it is for test, it is saying it is while training. This is during training. Please understand, this is not during, this is training. So during training, what it is trying to say, it is saying that this instance belongs to these 4 people are telling it is 1, and this one person is telling it is 2. So the logic of voting classifier is to count the number of votes. So here 4:1, so the majority prevails, so it is 1. So this is the logic of a voting classifier. So here let's go back to our notebook and see how exactly it is. So voting classifier, so the same thing in text form, whatever I've explained is there. You can read this later. You have hard voting and soft voting, all that. So the same thing here, predictions, new instance. Let's go back to the same slide I have taken here. Let's import this. So I am importing voting classifier. Along with that, I am going to take 3 more people, because I am going to choose between logistic regression, support vector machine, or a support vector classifier. Then I am going to take decision tree classifier. I am going to run all these 3, and I am going to take majority. The voting classifier is going to take majority of these 3. So let's run this. So we are going to import this first, right? So once it is imported, go and predict it. It did this. Voting it did. We have already done this 2-3 things. So we go and predict it on our data set, on our test set. We want to see our results. So we go down. See, your results are here. 73rd, same rows we have taken 18, right? 118, 78. Again, accuracy is good. Very good. So let us evaluate the performance of our model. So here confusion matrix and accuracy score. So we are importing these 2, and what we have to feed this, test signal and prediction. But now you are going to take the voting prediction, not the individual classifier prediction, voting classifier's prediction. Then again accuracy score, voting classifier. So you do this, you run this for the voting classification problem. Here you get, again you are having an accuracy which is 1. So here this is what is your part here. Okay, so what I'm trying to say here is, whatever was told, now let us come to technical part. I'm just stopping sharing my screen for 2 minutes. What I'm trying to say here is, yesterday we had looked about notebooks in the evening, late evening when we stopped. We saw decision tree, logistic regression, SVC classifier. Right? What is the accuracy that we saw? We saw that the accuracy is around 96 point with 1 misclassification we saw. So individually, if you run classifiers, then they are called non-ensemble classifiers, non-ensemble. Okay. And when we combine it together, that let us use all these 3 people. Let's see what this does. Let's see what this does, and let's see what this person does. And based on this, then I will decide what is the correct label. So if you are doing this, then you are into ensemble methods. So all of these are research topics, ensemble methods, non-ensemble methods. So many people would have this question, hey sir, how do you understand which classifier to use? You may ask me this. Okay, yesterday I showed you 3, there may be 20. How you decide which classifier? Common knowledge. We use it on different problems. We see that this is text recognition. We see that this is this recognition, that recognition. Then we see that, okay, this is this. Right? So this is how we are going to learn into classifications. This is how we are going into slowly into machine learning. So we have not yet gone into our cross validation, all those concepts, because we are starting one by one. So today we have gone into CNN. So quickly I will tell you, I had told you that I am going to tell you some other things, an important part, because not every time it is image. It is meaning for text also. So I'll just show you one example here. This is also one of the talks that I recently gave as part of National Science Day, the Girl Child Day I have given. So I'll just show you one of the examples where we have shown it is not necessary that we learn everything from image processing. No, though I belong to image processing, computer vision and all that stuff, but it doesn't mean that everything is image processing. So I'm just sharing my screen again to just show you one of the examples which we took to tell you that this part. So I'm putting share screen again, because one should have proper understanding of concepts. Okay. Yeah. So I think this is one of the this DST sponsored workshops that I gave recently. So here I want to tell you, see, this is what it is. Here examples I want to tell you, see, object recognition, millions of car images. So we'll see what and all traffic light it has recognized. Object recognition problem, who are in computer vision know. Traffic light means what, truck means what, car. You feed all these people, give it to a neural network, a deep network, it will tell you all the labels. Nowadays, ensemble neural networks are available, ensemble ADA boosting is available, all those things are there. I'm just telling you basics. So object recognition in images, you give thousands of cars, it will tell you that it is the car. Then you go here. This is one of my recent students who graduated with a PhD. So he was writing me one mail wherein he was asking me to tell about some journal got accepted, his journal got accepted, and we were trying to address the revisions. So when I saw this mail of his here, you see all of us would have seen thanks a lot on the bottom. If you see here, my suggestions before I can write him the, so here my suggestions are already there. Okay, I will check. So what he was trying to say is, I am sending you, sir, 2 points for last and give me suggestions. I am attaching the word file. Who has read this? Why these suggestions are coming here? It means here, this is my Gmail. So this means that the Gmail is reading all our stuff. It doesn't mean that there are some physical persons who are reading this mail. It is a machine learning, it's a natural language processing, NLP. We'll go about this little bit later. Natural language processing here, where these sentences are broken down and trying to understand by the deep learners. And for these sentences, the answers, typical answers are like this. And if I click one among them and send, then learner will become more strong. It will tell that if this is the question, this is the answer. Right? So it will learn more, it will better, it is using our data. Though there are security concerns, etc., still we are not going into that ethics and secure and all that Professor Barni will be talking today again. What I'm trying to say here is text recognition and analysis. Not necessary here, this is not any image, but here again a deep learner is there, but it is analyzing text data, right? Similarly here video analytics. So here I think this is taken from the Kharagpur campus. So here if you look at this particular 3 videos are there here. So I'll just escape so that I can play the video. So I'll just escape this. So if you look at this video, these were captured during my PhD. So this is also into video analytics. So here you could see that this is some stable, unstable videos which have been captured at Kharagpur campus. So here if you look, it has gone through stabilization, right? Stabilization. Though I have used non-deep learning based method in those days, this was early, late 2000s till 2010, 12, deep learning was not coming because Lee Kun was never being respected in the community, right? By the time Lee Kun was respected and the people came, I finished my PhD, right? But we tried to do these problems again at our lab and we got good results. And you look again, this is taken at Kharagpur campus. Those who know Kharagpur know this as the Tikka junction, right? So here if you look, this was taken by one of my, I and my lab mate were there in this particular area where we wanted to test, because my supervisor was telling me, you did video stabilization, yes, right? You stabilize the video, where you're going to use it? He was asking me. Every time I was asking, he was telling where you're going to use. He told, unless you tell me where you're going to use, you will not get your PhD, right? So this is what he told me. Then I one day thought where I'll use it. See here. So the logic is entire video is not unstable. Entire video portions are unstable in this entire video. So here see, these are all good portions. They are moving. Only certain portions are shaking, right? Here again it is shaking. So now my logic to him was, I showed this video and I told him that I will do selective video stabilization. Those were still non-deep learning days. Please see my logic. I use neural network, yes. Backpropagation trained neural network, I did use. This is my own work. I did use, but I showed this to my supervisor, my sir there at Kharagpur, and told him that, sir, whatever I did here and got these 1 or 2 papers, na, I will try to use it here. How? He asked me, sir. I said, I and my friend went today morning to Tikka Junction. He asked, did you go for tea? I said, no, I went with this camera and my friend and we took some videos. I'll show you. He saw this video. He said, what is there in this? He said, sir, I told that I will selectively stabilize. I will understand. So what I'm trying to say here is, so I'm bringing my pen back. For this video, I will do intelligent stabilization. Artificial intelligence, na? Intelligent stabilization I will do. What does it mean by intelligent stabilization? In this 5 or this whatever 1 minute video, I will select where there is unstable part. I will not manually do it. My algorithm will do it. Machine learning algorithm will find out where there is this shake, and then it will try to remove using my own algorithm. Then he said that if you do this, then your PhD is over. Go. Then of course I took 6 to 8 months more to do that and show and get the results. But this is what I'm trying to say, that it is not always image. It can be videos, it can be text, right? It can be something called forensics, which Professor Barni is doing. So here you see these 2 parts are there. Here this is superimposed from somewhere. So forensically you want to determine whether this is the original photo, whether this is original photo, or somebody removed this photo and made this as original. We don't know. We don't know, right? So that we are going to learn in imaging or video forensics across the 5 days, whatever we have, and going to explore the security aspects to this. So I think this is, I'm not going to share the other part because it was meant for a different audience. So now I am just taking these 3 examples because it is right fit to what I'm going to tell here. What I'm trying to tell here is, we are trying to tell that need not necessarily be everything my own image or my own this video processing. It can be text, it can be share prices, it can be weather prediction, it can be atmospheric science, right? It can be food processing. You want to understand soil health from different places of India, it could be there. Only thing, only data. Our data is there, machine learner can start, right? And all these tools are available, you can start. So with this, I'm just putting back my ensemble methods. So this, whatever we learned, so it means when a group makes a decision, we are going to decide better than individual. That is what is the logic of ensemble methods. And it has worked. So here, let me show you, it is working. All these notebooks are working. So with this, I think it is 11:45. I think we'll keep some question and answers here. So my task was to start with a CNN, though I explained the entire CNN, but I couldn't do the entire CNN here. I have to start with my CNN study where I take MNIST dataset, but we are running short of time. It is 15 minutes to what I normally stop. So here, but I want to keep the question answer session. So I'm just stopping share to understand if anything is there, any of the participants want to ask, please feel free, unmute yourself and ask me. You can always use the chat also. I think, yeah, I have one question. Is it advisable to get 100% accuracy using MI? Does it lead to overfitting and small size of it? Yes. So we'll come to this as our collab notebook progresses. Generally, it is not very good to have 100% accuracy. No models are 100% accurate. Overfitting is there. I think people who are new may not understand all the overfitting, underfitting, all that. We'll slowly talk about it. And see, I can give example of overfitting. Maybe people who have who know this thing know that what is overfitting. See, you are having a simple problem, say algebraic problem. You are going to add some numbers, right? So you are going to add some 10 numbers. So now instead of using simple algebra, so instead of writing this number plus this number plus this number, you are doing something like this, that first 4 numbers I will add, I will keep some here, right? Then I will add this other 3 numbers and keep my sum here. Then I will take few more numbers and unnecessarily what you are trying to do is you are going to complicate things. So it's a simple model. See, everybody likes life simple. You don't want life to be complicated, right? So now if I start my accent and English accent where no Indians will understand, it's of no use. We have to be as simple as possible. Overfitting also is like that. Overfitting means you are going to simply unnecessarily on a data, you are going to try and build a very complex model. Why? Because of the fun of it, that okay, yes, I want to best model, it should work for this. See your data and classification. If it is simple, if your simple classifiers work, why you want to do this? So overfitting happens when somebody here tries to use unnecessarily complex models on simple data sets. So it will start overfitting. But at the same time, you can't use simple. So you want to draw an ellipse, you want to draw, so you have some points to draw an ellipse, and now you are telling that I am now going to use straight line to model that. That is also wrong. That is underfitting. So you know that the task is to draw an ellipse. So all of us know ellipse is like this, y is equal to x square, and now you are telling that I'll use a straight line, y is equal to mx plus c. Answer is no. There you are underfitting. So overfitting means you are having y is equal to x square. What you are doing is y is equal to x raised to 11 plus x raised to say 9 plus something. You are using this model on when your problem is y is equal to x square. So underfitting and overfitting are two common problems in machine learning which comes here. But we should know, with some experience in machine learning by using datasets, we will come to know whether it's underfitting or overfitting. And we come to a next term, which is generalization performance, that I plan to cover in my tomorrow's notebooks. So tomorrow's session from 9:30 we are doing it important. So that please, we'll do the CNNs and we'll do that. Next, I think if you could explain boosting once. See, boosting means let's forget our data science or machine learning. Let us forget. Let us come to real life. So what is boosting? So what is boosting is, say I have some students who are facing problems or a little bit weak. So I give them confidence by giving motivational work. Why you are not doing this work, right? If you do this, it's going to help you in this way. Right? You can. So what I'm trying to do is I'm trying to boost. What I'm trying to, then the person says that it's becoming difficult. Then what I try to say is, you break this problem into small parts and try to train individual classifiers on these small parts. Then combine this. So I am boosting because singly it is not able to giving me less accuracy. When I split it, boosting is I am doing this, this and assigning one classifier, then doing this, then doing this. Then I am going to see everybody together. Then I am going to say that yes, it is better. So I am trying to boost the confidence of the classifier in classification. Just the way I boost the confidence of the student whenever the student faces problem, right? So the other example, weak learners. Suppose I have 4-5 students. So one student is facing problem. Then what I try to do, I try to couple one more student with that student, right? And I say, hey, X, please help Y, and see whether it can improve, whether the accuracy can improve, whether that student can improve. So X and goes and Y goes and helps Y. Jointly they do some work. Whatever Y was facing problem is overcome by X, and this way it is the entire problem is solved. But not many time it works. In classifier also it doesn't work. Doesn't mean that every time if I use ensemble method works. It may fail. There are many examples of failure. I have only shown you examples of success, but it also fails. So here also with all students we tell that take this help. That doesn't work, then we say leave, go, right? So here also it is like this. Here also ensemble methods need not mean that it works. Ensemble methods may also fail. Then as machine learning engineers, we have to go and see some other methods, some other techniques. But as an engineer, we should have all our tools, single classifiers, collection of classifiers, neural networks, CNNs, and we should see what is our problem and then going to solve the problem. So this is the summary of today's. I just summarize. If there is no more questions on chat, okay. Yeah, I think we'll summarize this. I have last 10 minutes with me here. So the summary of today's thing is, I took you into AI, ML, DL, told you how not to use common things, which the jargon, that jargon, whatever we have, that ML, AI, I don't understand, etc., etc. So that I have told you how to remove that and have clarity on that. After that, I went and told you traditional learning happens, how feature crafting, then classification, then this deep learning, how it happens, only neural networks, CNN layers, then max pooling layers, all that stuff, then flattening, all that thing I have explained. Of course, I have not done the notebooks. tomorrow I reserve that CNN notebooks, because if I do the notebooks without telling you the theory and what is convolution, it's of no use. It again simple becomes some explanation just to give, just to tell something. It has to be told, that it becomes like that. I never do that in my classes. I always see that concepts are correlated with the numerical part or with the notebooks. In this case, it's notebooks, so I use the word notebooks. So then we have I have shown you theoretically how CNN works, how CNN is solved the problems, many complex problems, how it solved. So all that theory we did, and after that we went to some notebooks on ensemble, that collection of others are better than single, voting, bagging, boosting. All these are common, and I have shown you they are all one-line commands. I've taken simple notebooks so that I have run. Tomorrow's part we are reserving for doing the complex things of CNN notebooks. Tomorrow I'm not going to explain you theory directly. First hour 9:30 when we start, we are going with our CNN notebooks. Step by step I explain how it goes, how to plot, etc. And we are some things which I have left that will be covered tomorrow there. So with this, I think it's almost coming to an end, this particular session. The task for today, as we know, we start again with Professor Barni today. So as I have told, it is in the evening session. So here we are trying our best to see that. I think I have our evening session starts at 17:30 India time. So it is 5:30 in the evening. So for Professor Barni, it would be at 1 o'clock. So I have shared the slides today. So I have shared the slides yesterday evening. I have shared. So whatever he is going to cover is being shared, and some parts whatever he is going to cover is also going to come in my notebooks little bit later. So this is 5 days. We are in day 2. So please reassemble back here today at around at 5:30 sharp, because we are on tight schedule. He's a foreign participant, and we don't want to waste much time from his part. And we want to see that it goes up till 8:30 is what he has told us. We'll keep it from 5:30 to 8:30. So with this, I thank you for joining. I'll be leaving the meeting. So I think I have one last question to take. So I think I have, what is the guarantee that max or average on pooling gives the best representation, subsampling with a reduction, but provide the name max pooling? Okay. Yeah, there is no such guarantee here. Max pooling many times is a commonly used. It works in all. Average pooling also works. So max and average are the two frequently used. So as machine learning engineers, what we do whenever we have some problem, we give that max pooling we see, we change the pooling, we make it average pooling, we note the accuracies. If both are same, then we can adopt anything. But if one is better, maximum number of times we have seen, my observation with whatever data I have worked, max pooling works good. So it is just a choice that max pooling works. So we can use max pooling, but it's not necessary that you should always use max pooling. You are a many pooling methods. What is important is pooling, whether it is max or min, that all depends on what application you are using. Okay. So I think that is not there is no such guarantee. It is coming out of experience with our data sets. So I hope I am able to answer you. Is it okay? Yeah. So this is there. Then I think we meet today again with the mathematical part. He's going to cover the security aspects. I'm also going. See, it's very important to attend, because if you miss somewhere, then you lose you lose that track. So let us not miss all the parts. Let us be, even I become ready now. I am not able to record properly or mute, because I am just talking here. I don't have control. My administrator is doing it. But when it happens for Professor Barney section, these sessions, I myself am fully glued and listening to every word what he's saying, because it's an experienced researcher and they feel whatever he's doing, and publishing is for next 5 to 10 years. That will be the one which will be there. So I request you to be on time at 5:30. We meet. Until then, please have a nice day. Thank you for joining. Bye bye. So I'm ending the meeting here. We'll again assemble back. So I'm stopping the recording.
हाँ এই কোশ্চেনটা পড়ো নাম্বার 2টা না নাম্বার 2টা
So good afternoon to Professor Barni and Namaskar again from India. And good evening to all the participants who are slowly joining. So we are into day two. So before we start the session, I just want to tell about the GIAN program, the Global Initiative for Academic Networks, which is an initiative launched by the Government of India so that Indian researchers as well as faculty members could do the things. I think there is some disturbance here. Let me check at this here. 1 second. Yeah. So I think we will just go through our part. So sorry for this. There was a disturbance. There was echo of the voice. So here, so what is going to be told here is today we are into day two, and I was talking about the GIAN program. So GIAN, as we know, is being supported by Government of India. So I'll just before the participants are slowly joining, so I'll just share a video where the importance of GIAN is told in terms of a video which the country has made and want. So I'm sharing my screen.
Education is our passport to the future, for tomorrow belongs to those who prepare for it today. And to develop the young minds for the big tomorrow, Ministry of Human Resource Development has come up with an international level global initiative for academic networks or GIAN in higher education.
My name is Barni. I am a fourth year PhD student with Professor B.C. Tripathi at School of Life Sciences, JNU. I took up a course on photosynthesis. It was being taught jointly by Professor Govind, who was an emeritus professor from Illinois.
To expose the students to international standards of teaching, this progressive initiative, GIAN, was officially launched on November 30th, 2015. It taps the talent pool of scientists and other academicians internationally to encourage their engagement with the institutes of higher education in India, such as IITs, IIMs, Central Universities, IISc Bangalore, IISERs, NITs, and IIITs. Conduct of about 478 international courses under GIAN is a thoughtful activity carried out by the host institutes. About 85 international professors are at present teaching the courses and conducting workshops to bring in fresh global perspectives in knowledge and understanding. Barni and other students, like her, have been trained under Professor Govindji, a renowned scientist who hails from University of Illinois, US.
Hi, I'm Sagarika Jaiswal. I've been in JNU for a year now, and I'm pursuing my master's in life sciences. So I'm really thankful to the MHRD for taking up this initiative and
This initiative is successfully garnering the best international experience into our systems of education by bringing in global exposure for students while being in India itself. GIAN is implemented to incorporate world-class faculty to teach in India.
I would really like to thank the MHRD for taking up this initiative.
I'm very happy that now Ministry has understood the need of such a program and it has started this.
I'm really thankful for MHRD for bringing forward this GIAN program.
Transforming India under the leadership of Prime Minister Shri Narendra Modi.
Yeah, so this was what was GIAN. So GIAN, as I told, is an initiative launched by the government, and one of the beneficiaries is myself, because we have with us Professor Barni, although not in the physical mode, though it started in 2016, so we are in 22. The last 2 years, GIAN has not made much progress because of the pandemic, and I think all of us have not made much progress because of the times that we are in. So without taking much time away, so Professor Barni, I think today morning was my session wherein we introduced the participants to simple notebooks, ensemble classifiers. So these were the things which were covered today. Introduction to CNN was given. So tomorrow morning we are going ahead with the CNN architectures. So now, as I have already circulated your slides to the participants via email, so your slides are already there with the participants. So as we know, the plan for the day is source identification game, and the preliminaries that you did yesterday would be elaborated and told in a more in the elaborate fashion along with some examples. So that's what is the plan for the day. Without taking away much time, I hand it over to you. So it's your day again. So it is over to Barni, Professor Barni. So thank you again for joining us today.
Okay, thanks to you for the introduction. And it's good that you already have the slides available so that you can take notes on them, and I mean, maybe it will be easier for you to follow me. So, so this was, oh no, one moment, I have to share the slides. Share screen. Share screen, where is it? Okay, here. Can you see it now?
Yeah, it is visible, yeah.
Okay, now, so this is the first page. So this is the, I mean, again, the outline of the general course. And today we are in day 2. So basically we are doing this part. And after giving the motivation and general intro, I already gave you an introduction to game theory. I gave an introduction to the method of types, which is the mathematical tool that we'll need to introduce at the games today. We are ready to put the ideas that I introduced yesterday at work. So, source identification games. Okay, so what I will do today is not only useful to know these games and the result of this theory, but also as a general methodology that you need to follow if you want to apply game theory to an adversarial problem. Because basically, I'll write it here, you have to do several steps. And the steps are: 1, you need to define the structure of the game. So in general words, you have to define which are the players and what they know, who move first, if they move together, and this kind of stuff. Second, you have to define the set of strategies. Available to the 2 players. Third, you have to define the payoff of the game, which means you have to define which are the goals of the players. 4, you have to find the equilibrium points. If this is possible. It's not finished, because the equilibrium point will tell you which are the satisfactory moves that the players can play. 5, you have to compute the payoff at the equilibrium. And the analysis of the payoff at the equilibrium will tell you who wins the game, or at least the payoff that the 2 players can get from the game under adversarial conditions. So what I will do today is that I will define 2 or 3 games, and then I will take at least the first of them and go through these 5 steps. And then at the end, when I arrive at step 5, I will use the payoff at equilibrium to understand who wins, in a certain sense, the game under certain conditions. So I will start, and I will spend much of the time today explaining the source identification game with known sources. It will be clear what I mean with these known sources later. And then later on in the class, I will also introduce two other kinds of games where the sources are not perfectly known. But to warm up our engine, I will talk with this SAI game with known sources. So, as I said, the first step requires that we define the overall structure, the overall idea behind the game. And so, in the source identification game, the structure is the following. I have two sources of information, X and Y. These two sources produce sequences of outputs according to a certain probability mass function, according to certain probabilistic rules. And P of X is the probability mass function of source X, and Py is the probability mass function ruling the emission of symbols from source Y. The defender take one sequence and must decide if this sequence has been drawn from X or not. So there are two sources, but the goal of the defender is to take one single sequence and decide if this has been generated by X or not. So like saying, I observe an image and I want to know if this image was taken by a certain camera. I hear a speech and I want to know if this speech was given by a certain person, or this kind of stuff. What about the attacker? The attacker, one moment. The attacker will take a sequence drawn from the other source, Y, and modify it so that the sequence seems to be taken from X. So I want to take a sequence from another source and pretend and claim that this was taken by X. To do so, the attacker can modify the sequence generated by Y up to a certain distortion. Otherwise, this is too easy. So I want to modify. So the idea is that suppose I want to understand is if a certain image was taken by a certain camera, then the attacker takes another image taken from another camera and modifies this image in such a way that this seems to be taken from the camera X. Or I want to know if a certain image was taken by a camera. I have an image generated by GIAN, and then I modify the image so that this image seems to be taken by a camera and not by GIAN. Good? Great. In the following, I will assume, at least at the beginning, that the sources are known. That is, the two players have perfect knowledge of Px and Py. Good? It may be strange to assume that D knows Py because Py is the source available to the attacker, but we need it to define a valid game. I will relax this assumption later. I also assume that the attacker knows perfectly X. This may be, a strong assumption, but for sure is a kind of worst case assumption for the defender. So assuming that the adversary knows everything about the source have to decide on is a worst case assumption. Great. Then I have to define the structure of the game. So is this a sequential or a strategic game? That is, can we assume that one of the two players play first and then the other plays knowing the move of the first? Or are we going to consider a strategic game where the two players work together, make their choice independently, simultaneously? I will assume a strategic game. And then there are other variants. there could be games where there are several moves, or the attacker could attack sequences from both X and Y. This is not the case here. As I said here, the attacker takes a sequence from Y and modify it. So sequences from X are never modified by the attacker. There are other variants of this game where the attacker can also modify sequences taken from X. This will not be the case here. Good. So now here we have the general structure of the game, and we have to define the game more carefully in a mathematically sound way. So the second step usually is to decide the set of possible moves, the strategies available to the defender and the attacker. In general, we want to have this set of strategies to be as large as possible, because we cannot confine the defender and the attacker to use a limited set of strategies. If we want to be as close as possible to real life, it's good to have this set of strategies as large as possible. And even more importantly, it is important that we do not limit much the set of strategies available to the attacker, because the attacker does what he likes. You cannot say the attacker, you have to choose this small set of strategies, because the attacker usually is very free. So we want to keep this as large as possible. On the other hand, if we keep these two sets too large, then the problem may be unsolvable. So some restrictions are important. And preferably, we'll put restriction on the defender. Is another kind of worst case approach. Then, given the framework before, what is the strategy I want, which is the set of strategies available to the defender? The defender can choose any possible acceptance region. What is an acceptance region? Well, here I'm assuming you are familiar with hypothesis testing, otherwise everything is complicated, but nevertheless, if this is the set S of all possible sequences, the results of the test carried out by the analyst, by the defender, will be take on one sequence, decide if this sequence was generated by X or not. Take another sequence, decide if this sequence was generated by X or not. If I do this for all the points in the sequence space, I define a region, which later I will call lambda 0, such that for all the sequences inside lambda 0, I decide that the sequence xn comes from X. Sequences outside, no. I say that those sequences do not come from X. Good? This is in the end, what the defender has to do here. Carry out the test. Great. Lambda 0 usually is called acceptance region, because we accept the hypothesis that the sequence come from X. Good. Given this, the set of strategies for the defender are all possible acceptance regions. Which is like saying all possible decision rules. Well, this is indeed too much, subject to a constraint on false positive error probability. You know, again, I assume that you know hypothesis testing, but when you run an hypothesis test, you have to decide between hypothesis 0, In this case, hypothesis 0 is that the sequence comes from X, and hypothesis 1, where you do not accept hypothesis 0. And you may have two kinds of errors. You may have a sequence coming from X, and you decide that it doesn't. So you decide H1 when H0 is correct. In our case, I say that X does not come, the sequence does not come from X while it does, and this is called a false positive error. Or I may decide, I may have a sequence produced by Y and then attacked and say that this comes from X. This will be called a false negative error. Good? Well, usually in hypothesis testing or decision theory, you have to balance the two error probabilities. You want to have both a false positive error and a false negative error probability. The problem is that these two errors are opposite. Usually, if you decrease the false positive error probability, you increase the false negative error probability, and vice versa. If you decrease the false negative, you increase the false positive. So a common approach in decision making or detection theory or hypothesis testing is to fix, to constrain the false positive error probability and try to do your best on the false negative error probability. So when I decide the set of all possible strategies for the defender, I say all acceptance regions, but constrained to have a certain false positive error probability. Is a kind of Neyman-Pearson criterion. Good? So this is still very, very general. Then I will include some limitations, otherwise the problem is not manageable. I will introduce some limitations on the kind of analysis that the defender can carry out. So not all possible acceptance regions will be possible because I put some limitations on the analysis of the defender. Eventually, in this game, I will focus on an asymptotic analysis. That is, when the length of the observed sequence xn tends to infinity. It is when, suppose I observe x1, x2, x3, xn, the results I'm going to derive hold when n tends to infinity. That is when I can observe a sufficiently long sequence of outputs from the source. Great. This is for the defender. And what about the attacker? The attacker, I do not want to limit the attacker too much, so the attacker can do whatever he wants, the only constraint being the maximum allowed distortion introduced by the attacker. Any attack is possible, assuming that the distortion it introduces is smaller than a certain quantity. And this distortion can be measured according to a kind of distance. So this is the general idea. Then let me translate these into equations. Here. So the set of strategies for the defender, SD, are all possible acceptance regions such that the probability of a false positive is smaller or equal than 2 to the power of minus lambda n. What does this mean? This means that the false positive error probability tends to 0 when n goes to infinity exponentially fast. With exponent at least equal to lambda. So I want that the error probability of the first type, the false positive, decreases exponentially fast. And the exponent of the exponential function must be at least lambda. Great. So the larger the lambda, the faster the false positive error probability will decrease. I want that this is at least lambda. Good. So this is the constraint on the false positive error probability. Then, and here you have the theory that I said yesterday, lambda 0 must be a union of type classes. This is the crucial requirement here. Let me try to explain. You may remember what a type class is. Given a sequence, so suppose for simplicity, I continue using binary sequences, okay? But all the analysis is not restricted to binary sequences. I take a sequence. Good. The type is the fraction of zeros and ones I have. In this case, 4, 6, 8, 2, 3, 7, 8. I have 9/18 zeros and 9/18 ones. And this is 0, 5, 0, 5. This 0, 5, 0, 5 is the type of the sequence. Good. Then the detector, the defender, takes this sequence and wants to know if the sequence is produced by certain source X or not. So for instance, X could be a Bernoulli source, that is a source producing independent binary variables with probability, you don't know, 0.9, meaning that the probability of 1 is 0.9. Then the defender must say, is it possible, can this sequence have been generated by X, where X is a Bernoulli, where the probability of 1 is 0.9? Very likely no, because if the Bernoulli is 0.9, I expect to have much more ones than zeros. Good? So, based on these observations, X must decide if this sequence comes from the Bernoulli source or not. Well, he must do this for all possible sequences, but the constraint I'm putting here is that if I take another sequence of the same type, that is another sequence with the same percentage of zeros and ones, that is, for instance, if I take this sequence, the decision of these two must be the same, because the acceptance regions must be a union of type classes. I either consider an entire type class inside the acceptance region or not. I cannot move single sequences in and out. I have to consider this as a union of type classes. So if I accept this one, I must also accept this other. You can interpret this in other two ways. One is you only look at the type of the sequence. That is, you only look at the number of times that the various symbols appear. I have to decide only, in this particular case, based on the number of zeros and ones, not on their position within the sequence. I only care about the number of zeros and ones. Call this an histogram. You can call this an histogram if you want. I'm taking my decision looking only at the histogram of my sequence. Two sequences with the same histogram will result in the same choice, in the same decision. Where these images? Two images with the same histogram could be judged exactly in the same way by the detector. Is this reasonable? Yes, because I forgot to say here that my sources are memoryless. Since the sources are memoryless, it makes sense to consider only the histogram or the first order statistics of the sequences. You can see this also in another way. When you keep the number of zeros and ones, or when you keep the histogram, what you can do is that you can permute the sequence and the histogram will not change. So saying that lambda 0 is constrained to be a union of type classes is equivalent to saying that your decision is invariant to permutations. If I take a sequence and permute it, the result of the decision does not change. Again, this is reasonable when the sources are memoryless. Good. So this is the set of strategies of the defender. Now what about the attacker? The attacker the set of strategy of the attacker is the set of function f that transform the sequence y, so a sequence taken from the second source, into a Zn, which is equal to this function of Yn. So the set of strategies of the attacker is very large. All possible functions transforming a sequence from y, that is generated according to P of y, into another sequence, Zn. The only constraint is that the distance between the original sequence and the modified attacked one should be lower than nd, where n is the length of the sequence and d is the maximum average per letter distortion. That's it. Very simple. If you look at this, you will see that here I'm constraining more the defender than the attacker. And this agrees with what I said before. In our analysis, it's better to take a worst case assumption where we put some limits on the defender. The attacker will do what he likes. Now, here you also see that it is necessary that A and D know P of X, because in a complete information game, the two players must know the set of strategies. And in order to compute the false positive error probability, that defines a set of strategies available to the defender, I need to know P of X, because this will depend on how the sequences are generated from X. So this is the second step in our framework. Define the strategies. Third step, we have to define the payoff. I will adopt a zero-sum game. So the payoff of the defender and that of the attacker will be one the inverse of the other. And this is pretty clear now. I said that the defender has to observe a certain probability of false positive, and then he will try to minimize the false negative error probability. So the defender fixes the false positive exponentially and tries to minimize the false negative error probability, that is, the probability that the sequence generated according to Py is judged to be taken from X. So PFN. Of course, the defender wants to minimize PFN, while the attacker wants to maximize PFN. Because the idea is that I take a sequence from Y as an attacker, and I modify it in such a way that this seems to be taken from X. So I want to induce a false negative event. So the payoff for the attacker, UA, is the false negative error probability, while the payoff for the defender is minus the false negative error probability. So that both of them want to maximize their payoff, but this results in maximizing the errors for the attacker and minimizing the errors for the defender. Good. And you see from here that this payoff depends on both the decision rule chosen by the defender and the attacking function f chosen by the attacker. And so the payoff will depend on both the choices of the two parties. And this is the formula. The probability of false negative is the probability that Y generates a certain X such that generate a certain X summed over all X's such that after the attack this sequence belongs to lambda 0. So I have fixed lambda 0. I have fixed F, and then what I do? I generate one sequence from Y, because you are considering the probability of false negative. So the probability of false negative is equal to the probability that I decide for X, given that the sequence comes from Y. So I generate a sequence from Y. This is this probability, and I want to know if after the attack this enters lambda 0. And I will sum the probabilities of all the sequences for which the attack succeeds. And this will give you the false negative error probability. Very clear, very rigorous, no chance of making errors here. And from this formula, you see that it happens what you want. The false negative error probability depends on lambda 0 and depends on F. So it is a result of the choices made by the two players. Good. Remark. From here, you see that it's necessary that both A and D know PY, because otherwise they are not able to compute the payoff. And you see here that the payoff depends on PY. So since it is necessary that the two players can compute the payoff for any two possible choices, at this moment, it is necessary that both the attacker and the defender know the probability mass function of the second source Y. You will see later that is not necessary for A, but for the moment, this has to be done. Okay? The first step will be to study the equilibrium. But before doing that, until this point, we are not solving anything. We are simply defining the game. Is this clear? Do you have questions about the definition of the game? No? Now we will try to solve the game, so to find the equilibrium points. But in many cases, solving the game, and we will be able to do it, but in many cases, solving the game is difficult or even impossible. Does this mean that game theory is useless in those cases? No, it doesn't. Because a clear and rigorous definition of the game is anyhow important. What I did until now, until this third step, is as important as solving the game. Because one of the advantages, one of the good things of game theory approach is that it helps you to define exactly the problem you want to solve. Maybe you're not able to solve it, but you know exactly the problem that you want to solve. In the second step, I decided what the two players can do. In the third step, I define what the players wants to achieve. Then I'll see which are the best possible strategies to achieve this goal. But the definition of the game is already very, very, very important. Now we can do much better, at least in this case, because the first step will see, given the strategies, which are the best possible moves for the two players according to certain notions of equilibrium. Well, one of the main results in the theory that we have developed is this lemma. This lemma says that there exists a dominant strategy for the defender. What is a dominant strategy? I said this yesterday. A dominant strategy is a choice for the defender that is the best regardless of the defender. Sorry, I put it here. Regardless on A's strategies. What I've written here, and then I will try to explain it, is the best the defender can do for all possible moves of the attacker. This is dominant. So the kind of equilibrium that we will find is a very strong one. It's a dominance-based equilibrium point. So what does this strategy say? Remember, I said that I focus on a case when n goes to infinity. When n goes to infinity, this term here goes to 0. Because log n divided by n tends to 0. So for the moment, to understand better what you're doing here, don't consider this part. Consider only this part. So what I do here? I take a sequence xn, I compute its empirical probability density function. So how many zeros and ones I see in my sequence, for instance. And then I compute the Kullback library distance from the source P of X that I want to analyze. If the empirical probability is too different from what I should see from a source X, then I will not accept the fact that Xn comes from the source X. So I will accept hypothesis 0 only when the distance between the empirical probability of Xn and X is smaller than a certain lambda, which, by the way, is exactly the lambda that defines the set of strategies. But before understanding why I have lambda here, let me try to show you the meaning of this. The meaning is pretty simple. I will use again the example of the Bernoulli source. Suppose I have a Bernoulli source 0, 9. So I expect the sequences by the law of large numbers when n goes to infinity. I expect sequences to have 90% of ones and 10% of zeros. Then I observe this sequence. In this sequence, the empirical probability of the sequence is equal to 0, 5, 0, 5, while this was 0, 9, 0, 1. Is it reasonable that this source produces a sequence with an empirical probability which is so different than the source? Well, I compute the divergence between P xn, this, and this Bernoulli 0, 9. If this is lower than lambda, great, I accept. If this is not lower than lambda, I don't accept. So this is a kind of divergence-based detector. I decide on a sequence if the divergence is smaller than something. If what I observe is close enough to the source. And remember, this is a kind of distance. So this is like saying that I accept xn being generated by x if the distance between, if the Kullback library distance between pxn and px is smaller than lambda. Good? It makes sense. And this is a type invariant, because if I permute my sequence, the percentage of zeros and ones does not change, and so this Kullback library distance will not change, and so this lambda 0 will be a union of types. The important results here is that this strategy is dominant for D. This is the best D can do, regardless of what the attacker does. And interesting, even regardless of Py. There is no Py in this rule here. This rule depends only on P of X and lambda. So this is optimal, also regardless of P of Y. And hence, at the beginning, when I said that the defender must know P of Y, this was not correct. It was necessary at the beginning, but in hindsight, after having demonstrated this lemma, then this is no more necessary. the optimum decision rule can be applied even if we do not know the probability of y. Okay? Now, where does this come from? Let me see if I can insert one page here. Can I? No, I can't. Don't have the pro. So let me see if I can find one empty page. Okay. This is enough. Okay, good. So what is the idea? The idea is the following. Annotate. This is the set of possible sequences S. I remember I said this yesterday, I can split this set of all possible sequences into types, into type classes. Some of them are big, some of them are small. This is T1, this is T2, and I have many. And each of these has many sequences inside. Remember, what I have to do here is that if I want to, when I have to define lambda 0, I have to consider lambda 0 as a union of type classes. So if I want to paint in yellow lambda 0, then I have to take or don't take entire classes. I cannot take or not take single sequences. My region will have to be a union of type classes. This will be my lambda 0. Union of type classes. Great. And then what I have outside will be lambda 1. Which is lambda 0 conjugate, the complement. So let us consider now, and of course, P of x will be inside it. This will be P of x, for instance. Good. Now, for the false positive, the probability of false positive is that something generated from P of x goes outside. So from the point of view of P of false positive, I want lambda 0 to be as large as possible. Because if this is larger, then it's more difficult, it's more unlikely that something goes out. This for PFP. But what about the attacker? The attacker takes something. Suppose this is P of y. Takes something generated from P of y and wants to move it inside lambda 0. So the larger is lambda 0, the easier will be for P of y to enter lambda 0. So from the point of view of the false negative error probability, it is better that lambda 0 is as small as possible. So you see here, I had to find a trade-off. Increase lambda as much as I want. No, sorry. Make lambda 0 as small as possible, because this is my payoff. Remember, the payoff was the false negative error probability. So if I want to optimize, when I say I mean the defender. If I want to optimize the payoff, I need to make lambda 0 as large as possible. No, sorry, as small as possible. But can I make this incredibly small? No, because if this is too small, the probability of false positive will increase too much. So I want to make lambda 0 as small as possible, subject to the constraint that the probability of false positive is smaller than 2 minus lambda n. So what? The idea is that I add to my lambda 0 yellow types until I reach exactly 2 minus lambda n. At that point, I stop because I reached my constraint and lambda 0 is as small as possible. Let us go back. And this is the first perspective, but there's more here. Now, what does happen when I add a new type to lambda 0? Well, how much is the probability under X? Suppose this is type I. How much is the probability that X generates a sequence in Pi? We know it. We saw this yesterday. This is more or less 2 minus n divergence between the probability of the type and P of X. Good? So what I will do is that whenever I add good. So this is the probability. Then what? The probability of false positive will be the sum over all the types that do not belong to lambda 0. So I start from P of X. The probability of falling outside is the probability of all the types that do not belong to lambda 0. So it's the sum of all the types that do not belong to lambda 0, the probability of the type, that is 2 minus n d P of t px. And I want this to be smaller, not equal, than 2 minus n lambda. Good? Okay. So if t is such that the divergence is smaller than lambda, this term only put in the summation is enough to make this inequality wrong. I'm summing many exponentials here. If even only one of those exponentials is smaller than lambda, because I have a minus in front, then this itself is enough to make the false positive constraint fail. So it is necessary that I put inside lambda 0 all the types for which the divergence is smaller than lambda. Otherwise, the false positive constraint is not satisfied. So this means that it is absolutely necessary to satisfy this constraint to include inside lambda 0 all the types, that is all the sequences, whose divergence, whose Kullback-Leibler distance from Px is smaller than lambda. If even one of those is outside, force positive constraint is not satisfied. Good. So what I will do is that I will introduce in lambda 0 all the types for which this divergence is smaller than lambda, and only those, not even one single more. Okay? Why not one, not even one single more? This is the last part I have to explain. If you understand this, then everything will go well. The idea is it enough? Is it sufficient that, let me explain. Is it sufficient that lambda 0 contains all types such that the divergence between the probability of the type and P of X is smaller than lambda? Is it sufficient? Couldn't be the case that all the types that are outside all together, summed all together, give a probability that is larger than 10 to minus m lambda. Suppose lambda is equal to 10. I want the error probability to be smaller than 2 to minus 10n. Good. Suppose this type has a divergence equal to 11. This other has a divergence equal to 13. This other has a divergence equal to 12. Each of these types by itself satisfies the constraint because 10 to minus 11n is smaller than 10 to minus 10n. 10 to minus 12n is smaller than 10 to minus 10n. No problem. But what does happen when I sum all of them together? Each of these is enough. But what does happen when I sum all of them together? Because I will have sum over all the t's that do not belong to lambda 0 of 2, one moment, 2 to minus n divergence between t and p of x. Each of these d is smaller than 10, that is lambda. What does happen when I sum all together? Is it possible that summing many of them, then I do not satisfy the constraint anymore? No. And you know why? Because the number of types grows only polynomially with n. So at most, here, I will have a sum 2 to minus n d, which is the max d, no, sorry, the mean d, multiplied by n plus 1 this. But when n goes to infinity, the exponential part is by far dominating. The growing polynomial in front does not change the decreasing nature of what I have, and so I can add as many types as I want here, assuming that the exponent of the probability of each of these types is larger than lambda. These two things together prove that the optimum lambda is formed by all and only the types for which the divergence is smaller than lambda. And this is what I have in this lemma here. the optimum, and this reasoning does not depend on what the attacker does. This reasoning does not depend on P of Y. So you see here, lambda 0 is formed by all the sequences for which the Kullback library distance between the type of the sequence and px is smaller than lambda, and something else here that is needed for the proof, but these parts tend to 0 and n goes to infinity. Is at least the general intuition clear? If it is, then, I mean, here is the same stuff. If it's clear, then you can very easily understand the proof. Because the proof of this lemma is formed by two steps. First of all, I must show the correctness of the region. That is, I must show that this choice belongs to SD. That is, that the false positive is the one we want. And this is the proof. The false positive, if the sum over all the types belonging to lambda 1 is lambda 1 star is the complement of the optimum lambda 0. So I sum over all lambda 1 the probability of the type. And each of these is smaller than the maximum probability. So I can take the maximum of this probability in lambda 1 and multiply by the possible maximum number of types, which is this polynomial. The maximum probability of the type is 2 to the n minimum divergence among all the types in lambda 1. And this minimum divergence is larger than this quantity by definition, because otherwise P would not belong to lambda 1. If I put this and bring it to the exponent, I take this formula, where I have now a 2 in front here, but an n goes to infinity, this part doesn't matter, and this tends to 2 minus n lambda, meaning that this decision rule here is asymptotically correct. And then the optimality means that if I have this, if I choose another lambda 0, then the lambda 1 I get is contained in lambda 1 star, which is lambda 0 star complement. And if this is the case, then no problem, because I said before that for the false negative point of view, the larger the lambda 1, the better. So if for any other lambda 0 that result in an acceptable false positive error probability, the lambda 1 is contained in lambda 1 star, then this is optimal. And the proof is even easier now. So let lambda 0 be any other decision rule for which the false positive constraint is satisfied. And let P be a type belonging to lambda 1. Then, since lambda 0 is in SD, the probability under X of lambda 1 is smaller or equal than 2 raised to minus lambda n. The probability of the entire lambda 1 is surely larger than the probability of one single type inside it. And the probability of one single type is larger than this because T does not belong to lambda 0. And then P also belongs to lambda 1. And then this proves the optimality of lambda 1 star. Okay, regardless of the proof, the basic idea of the proof is what I said before, is based on the properties of types. Maybe the take-home lesson here, the most important take-home lesson, is that this is the optimum decision rule, the optimum asymptotic decision rule for the defender. And this is dominant. Good. Are we finished for the equilibrium? No, we are not. This is the optimum for the defender. I must find the optimum for the attacker. The optimum for the attacker, however, is very, very easy. Why? Because since the defender has an optimum dominant strategy, the attacker can assume that the defender will choose this dominant strategy. So this is sure. And the attacker knows that this is optimum. So the attacker knows that this will be lambda 0. At this point, then the attack can be tuned to attack the lambda 0. And since I decide based on the Kullback-Leibler distance between xn and p of x, the attacker is, I take a y from y, generated from p of y, and I modify it in such a way that the Kullback-Leibler distance between the transformed sequence and p of x is minimum. Because this is what I want to do. The smaller this is, the higher are the chances that the transformed sequence Z belongs to lambda 0. So the f will be a function that chooses the Z within the admissible distance, within the admissible distortion, such that the Kullback-Leibler is minimized. And this is obviously the optimum attack strategy for the attacker. And hence, these two strategies, this lambda and this f, represents the only rationalizable equilibrium point, or a dominance-based equilibrium point of the game. And this is a very strong result, because not only we were able to solve the game, but we were able to find a very strong equilibrium, which is the dominance-based equilibrium. In this game, these two are the best moves that the two players can choose. No better choice is possible. Is it okay? Do you have questions here? Understand that this is not very, very easy. I realize it. I'm going very slowly. I really hope you can get at least the flavor of what I'm doing. Do you have questions?
Yeah, I have one question here.
Please.
Yeah, with regard to the equilibrium, so will it reach the Nash equilibrium at some point?
This is much better than the Nash. This is stronger than the Nash equilibrium.
Okay. Okay. So Nash equilibrium becomes some sort of an average bound here. Am I right?
I mean, if you have a dominance-based equilibrium, this is also a Nash equilibrium. So
Okay.
The dominance property of the equilibrium is stronger than Nash. So this is also a Nash equilibrium, if you want. But it's something more than a Nash equilibrium. So it is a Nash, but better than Nash.
Okay.
Okay.
So are there any limiting conditions for this to hold good, to reach this equilibrium point?
I mean, this is very theoretical, but if the game is defined as this is exactly, the conditions are those in the game.
Okay.
That the defender relies only on the histogram, if you want, on the first order statistics of the sequence it sees.
So isn't the game tilted towards more the attacker than the defender?
This game is more favorable for the attacker than the defender. Yes, because we constrain the set of strategies of the defender, but we didn't constrain much the set of strategies for the attacker. So this is the way this game is defined is in favor of the attacker. So the idea is, if you're able to win the game in this setup, then great.
Means it's like an adverse condition which is being imposed and still the defender is able to defend, then it's a good solution. Am I right?
Yes, yes,
yeah,
exactly.
Great.
Yes.
Yeah, okay.
So I will continue other 15 minutes and then we make a break, okay?
Yeah, sure.
Okay, so last step, who wins? Now that we know the optimum strategies, we can compute the payoff with these strategies. So assuming that the two players do their best, who's gonna win this game? This part I simplified this a little bit. All the details are in the paper because otherwise it's too complicated. Nevertheless, the idea is, let me introduce this other set. And so look at this picture here. P of X is the source. The dark blue here is the lambda 0. And then what? I defined another set, which is this gamma, which is the set with all possible sequences, with all the sequences, such that it exists a Zn belonging to lambda 0, whose distance from Y is smaller than Nd. So if I have a sequence here, Yn, it means that there exists an Xn inside lambda for which the distance is smaller than Nd, which is the distortion that the attacker can introduce. If you are in this situation, the attacker will find this Xn, this will be Yn, this will be his Zn, and then the attacker will succeed. On the other hand, if the Yn is too far away, there is no Xn or Zn, call this Zn. There is no Zn inside lambda 0 such that the distance is within the bound. So the idea is simple. The definition is complicated, but the idea is simple. Sequences that are too far away from lambda 0 can never be modified in such a way to be successfully attacked. Sequences that are close to lambda 0 can be modified in such a way to be brought inside. Good? Well, here I'm speaking about sequences, but in fact, I should speak about types, because even gamma is a union of type classes. The idea is that, I will not prove this, but the idea is that if I have a sequence that can be moved inside lambda 0 by a certain distortion, all the sequences in the same type can still be moved inside lambda 0. Okay? So this gamma is the set of types such that for all the sequences in the type, it exists a sequence in lambda 0 star at a distance within the distortion bound. Then, forget this one. Then we have Sanoff's theorem. But don't care about Sanoff's theorem. I will simplify this as well. So, suppose this is your set S with all the types, with all the type classes. So P of X will be here. This Q is P of Y. Good? Then, is it possible, and this set here is gamma. Gamma n when n goes to infinity. So the asymptotic version of gamma. And here inside we have lambda. This is lambda, this is gamma, and then P of Y is outside. Is it possible that P of Y generate a sequence within gamma? By the law of larger numbers, no. All the sequences will have a very small distance to Q. And Sanoff's theorem tells you also how much unlikely this is, but I don't care about this. So if P of Y does not belong to this gamma, then with probability 1, all the sequences generated by Y will not be in gamma, and hence cannot be brought inside lambda 0. On the other hand, if P of Y is inside gamma, then with very large probability, I will generate sequences within gamma, and then these sequences can be brought inside lambda 0. So in other words, we can prove this theorem saying that given Px, this, given lambda, and if you have lambda, small lambda, I will define the optimal acceptance regions, because the optimal acceptance regions depends only on P of X and lambda. Given this, I can define this set gamma, which is the set of non-distinguishable region. And this will depend on D, because if D is larger, I can bring inside lambda 0 something that is more far away. Look at here. This is lambda. If D is small, gamma will be very close. If D is large, gamma will be very large, because I can travel a larger distance to enter lambda. So the dimension of gamma will depend on D. So gamma is a function of D and lambda 0. That is a function of D, lambda, and Px. Now, if Py belongs to this gamma, then the false negative error probability tends to 1 when n goes to infinity. If Py does not belong to gamma, then the false negative error probability will tend to 0 when n goes to infinity. So, what does this say to us about the winner of the game? It says that who wins the game depends on the position of Py with respect to Px. And this position given lambda, that tells you how big is this set, and given d, that tells you how much you can move to enter the region. If P of y is close enough to P of x, and close enough depends on lambda and d, if P of y is close enough, then no way the attacker wins. And it does not win by a small extent. The error probability will tend to 1. There is no intermediate case. The attacker will be able to attack the sequence with probability 1. So if Py is close enough to P of x, then Py wins, no way. On the other hand, if P of y is far from P of x, the defender wins. The error probability tends to 0. And it wins by far, because this tends to 0, and we also know that it tends to 0 exponentially fast, by the way. And we can also compute how fast it goes, which is this, but don't mind. So what I'm saying here, and we'll elaborate on this a little bit more afterwards, is that with these optimum strategies, there is no balance, there is no tie between attacker and defender. If the two sources are close, the defender wins. If the two sources are far, the attacker wins. No, sorry. If the two sources are close, the attacker wins. They are too similar. If the two sources are far away, the defender wins. What does it mean? Close and far? It depends on lambda. So how small should the false positive be? And d, the amount of distortion that the attacker can introduce. Not finished. What about lambda? Lambda tells you the size of the dominant strategy, because I will put into lambda 0 all the types such that the divergence is smaller than lambda. So if lambda is larger, lambda 0 will be larger. So the idea is that if this is what I have with a certain lambda, if I increase lambda, I will have a larger lambda 0. On the other hand, if lambda is smaller, I will have a smaller lambda 0. And if lambda 0 is smaller, even gamma will be smaller, because the target region is smaller, then it's more difficult to enter it. So from a certain point of view, if I want to decrease gamma and then making it easier for the defender to win, I should choose a smaller lambda. How small? Here I say that I'm happy with any positive lambda. Why? Because the false positive error probability is smaller or equal than 2 to minus lambda n. So when n goes to infinity, even if lambda is very, very, very small, assuming that lambda is positive, this PF will tend to 0. And it will tend to 0 exponentially fast. So in fact, I don't care about having a large lambda. Any positive lambda is okay. So what I will do is that I will take my lambda 0 star and let lambda go to 0. And then I will obtain the smallest possible lambda 0. And if this happens, lambda 0 star tends to px, which is obvious because lambda 0 requires that the divergence between p of xn and p of x is smaller than lambda. When this tends to 0, since the divergence is 0 if and only if these two are equal, p of xn will need to tend to p of x. And then when lambda tends to 0, lambda, you see it here, lambda 0 is equivalent to px only. This is the smallest possible lambda 0 star I can get. A small and infinitesimal neighborhood of px. In this way, gamma also decreases, and I get the most favorable game for the defender. This is the best the defender can do, because the false positive tends to 0 exponentially fast, and the indistinguishability region is the smallest possible indistinguishability region. Let me see what I have. Okay. Hope this is clear. So the best case for the defender is to use all this theory with an infinitesimal lambda, as small as we want. Good. Maybe we can stop here for a break. Otherwise, it's too complicated. You start losing me if you didn't do already. What do you think?
Yeah, we'll take a break here, I think. But before that, one last question here.
Sure, please.
Yeah, on this region, will there be any blind spots? Any blind areas?
No, because the divergence is a smooth function.
Okay, okay.
Because I mean, this region is defined in the. I mean, you have to consider this region as in principle, this should be in the region of sequences. But since you are considering only the first order statistics, this can be seen in the region of all possible probabilities mass functions. And in that region, the divergence is a smooth function. It is continuous, it has all good properties, so there will be no gap.
Okay.
Or at least, if you use Lebesgue theory, the measure of the gap will be 0.
Right.
Okay.
Sure. So thank you. I think we can take a break of, say, 15 minutes. Is it okay? 15, 20 minutes?
15 minutes is great, yes.
Yeah, 15 minutes we'll take. Yeah.
Okay, good. Hello.
Yeah, I think we are ready to start.
Yes, we can restart. So now, I hope we have some time to think about what I said, but let me summarize in 1 minute. So the idea is that given all the framework, given everything, I will choose a lambda 0 region, which is an infinitesimal surrounding neighborhood of Px. In the limit, we can say that my lambda 0 star will be equal to x, Px. That is, if n is very, very, very long, as soon as what I observe does not agree with the relative frequencies that should be produced by P of x, I will reject the hypothesis H0. Or suppose you have, I don't know, a fair coin, which is P of x. You observe a very long sequence, and you want to accept if this sequence was generated by a fair coin or not. As long as the relative frequencies of the very long sequences are not very, very close to 0.505, I will reject this hypothesis. The only way I can accept the hypothesis is that the relative frequencies of the sequence I see are very, very, very close to 0.505. How close? Well, when n tends to infinity, arbitrarily close, given that n is not infinity, can be as close as I want, but not 0. This is intuitive if you rely on the law of larger numbers, because of the law of larger numbers, when n goes to infinity, what I observe will be, I should be very close to the source, and if this is not the case, I can reject this hypothesis. Good. Now, since there is an attack, so this lambda 0 will be equivalent to P of x. Since there is an attack, there will be other sources, P of y, and if even when I have another source by the law of large numbers, I will only observe sequences very close to P of y, then the idea is it possible to modify this sequence so that the relative frequencies are those expected from P of x? The set of PYs for which this is possible give you the indistinguishability region gamma. The set of Ys for which this is not possible cannot be transformed. So again, another example. If P of x is a Bernoulli 0.5, if P of y is a Bernoulli 0.6, and D is equal to 0.2, then great. I have enough room to modify sequences with 60% of zeros into sequences with 50% of zeros. But if D is equal to 0.05, the distortion is not enough to make a Bernoulli 0.6 equal to a Bernoulli 0.5. Okay? Good. Now, you understand at this point that this indistinguishability region gamma depends on D. Because if the distortion, so given Px and Py, whether I can bring P of y to be equal to P of x or not depends on the amount of distortion I have. So the indistinguishability region gamma depends on D. If D, so, okay, the larger the D, the larger the indistinguishability region. So now, suppose you have a certain P of x and a certain P of y. If D is too small, then P of y will not stay inside gamma, and the defender wins. Always wins. If D is very big, P of y will be inside gamma, and the distortion is enough to bring P of y into P of x. In this case, the attacker wins. You can imagine, since everything here is continuous, that there is a limiting value of D for which this P of y is exactly on the boundary. This limiting value of D is called security margin in our theory. What is this? This security margin is equal to the maximum value of D for which Px and Py can be distinguished despite the presence of the attacker. In the first case here, P of y and P of x can be distinguished because the attacker has not enough power to bring P of y into P of x. In the last, no. Good. If D increases, this gamma increases up to a point where P of y is on the border. This will be the maximum distortion for which the two sources can be distinguished. We call this in our theory security margin. Said in another way, the security margin between two sources is the maximum distortion under which the two sources can be distinguished. Because in theory, without attacks, if the two sources are different, they can always be distinguished by the law of large numbers. But due to the attacker can bring them close to each other, and then there must be a certain margin between the two to make them still distinguishable despite the presence of the attacker. Good? Great. This margin is called the security margin, and is exactly equal to the maximum distortion that you can allow to let the two sources distinguishable. And this is a very nice, very interesting quantity, because all this complex theory, the game, optimum strategies, payoff at equilibrium, everything can be summarized in one single number, Sm. I give you two sources. You compute the security margin between the two sources. If the distortion allowed to the attacker is larger than the security margin, the attacker wins. If the distortion allowed to the attacker is smaller than the security margin, the defender wins. That's it. And winning means, for the defender, both error probabilities go to zero exponentially fast. And for the attacker, winning means that the false negative error probability tends to 1. So you see, this is a very powerful concept. One single number that summarizes everything of the game. And it depends only on the two sources and the kind of distance you're using. I guess you have one question here. How can you compute the security margin? This theory is so complicated that, I mean,
Professor
how can
Barni,
we come out?
Professor Barni, I have a question.
Sorry, yes, please a question.
This Px and Py could be any distribution, or there is our assumption that it is a fixed distribution?
There can be any distribution,
any,
but Consider that here we are considering the case of discrete sources. So they must be defined on a finite alphabet. They cannot be Gaussians, for instance.
Okay, they
The
cannot be
extension of these to continuous sources is a bit complicated.
Okay, so it should be a discrete one only.
Yes, that can be discrete, but can be anything.
Can be anything. Okay, so Px and Py may be a two different distribution, discrete distribution.
Yes.
Okay.
Any two different distributions.
Okay, thank you.
Good. So the question is, how can you compute this security margin? And here there is the last surprise of this theory. There is an elegant and very strong relationship between the security margin and optimal transport theory. Optimal transport theory is a theory developed in the 19th century, and it has been introduced as follows. Let us interpret Px and Py as two different ways of piling up a certain amount of earth. And let Cij be the cost of moving a unitary amount of earth from the ith to the jth bin. And by bin here, I mean symbol. The earth mover distance is the minimum cost necessary to transform Py into Px and vice versa. So this Cij, suppose you have an alphabet, and the elements of the alphabet are A1, A cardinality of the alphabet. Cij is the cost of transforming, of changing AI into AJ. So I have my sequence. If I transform a symbol AI into symbol AJ, I will pay a cost Cij. So if I have a binary sequence, could be the cost of flipping a 0 into a 1, or the cost of flipping a 1 into a 0. Good. This optimal transport theory gives you the cost of transforming a probability distribution Y into probability distribution X, assuming that you know the cost of transforming an I into a J. Well, it can be proven, it is in my papers, that the security margin between two sources is exactly this optimum transport that often is called the earth mover distance between two probability density functions. These mathematicians defined many years ago this earth mover distance between probabilities, and this is exactly the security margin that we want. So I give you two sources, I give you two probabilities, you compute this earth mover distance, and this is exactly the security margin between the two sources. If the distortion is larger, the attacker wins. If the distortion is smaller, the defender wins. By the way, this earth mover distance is also very common in computer vision, because it is the cost of transforming the histogram of one image into the histogram you want. So suppose you have an image with a certain histogram, and suppose you want to transform the image so that the histogram is the target histogram. And suppose that changing a gray level from a certain value to another is your cost. The earth mover distance is the minimum cost to transform one histogram into another. And this is exactly the security margin between the two sources. Is it easy or is it difficult to compute the earth mover distance? Well, there is one algorithm that for scalar sources, as we have, And for a very large class of distances, it's easy. There is a very efficient algorithm to compute the earth mover distance between two probability mass functions. In particular, if you have that Monge's property satisfied, that is, if the distance or the cost is in the form I minus j raised to p with p larger or equal than 1, like for instance, in the case of the square distance, so the mean square error, or the with p equal to 1, it is the absolute distance, then there is the so-called northwestern corner rule that can be used to compute the security margin. How does this work? This is the source PMF. This is the target PMF. You start with the smallest. So you suppose that your I and J, your symbols are ordered. Otherwise, you cannot compute this difference. So if these are your symbols, you start with the smallest value and you move the smallest values into the smallest values of the target. And then you know how much you have to pay. If the smallest, if the value of the target probability mass function is full before the source is finished, you move to the next, and so on and so forth. And if what you have here finishes before the other, you continue with the next. You do this, you compute the earth mover distance, and this is equal to the security margin between two sources. The cost you need to pay to move this, call it histogram, into this histogram by moving the smallest values to the smallest values. And this is very practical. You can find the programs to compute this earth mover distance all around the web. I mean, no problem. It's very simple algorithm. You can compute this in 2 minutes. And this closes the theory, which is very elegant, very nice, all summarized in one single value. You have a clear definition of the game, you have a clear definition of the strategies, you have a clear definition of the payoff, you have the optimum strategies, you have the payoff at the equilibrium. And then you can summarize everything into one single number, this security margin between the two sources. And this single number can be computed easily by relying on optimum transport theory, because this, in the end, is equivalent to the earth mover distance between probability mass functions. And so you give me two distributions, I compute this quantity, and if your distortion is larger, you win. If your distortion is smaller, I win. That's it. Very elegant, very, very interesting. And very theoretical, by the way. So, can you use this in practice? Not easy, but there are some cases where you can apply this in practice. And I mean, the easiest and most practical example comes from multimedia forensics, and in particular on histogram-based forensics. So suppose you want to develop a multimedia forensics algorithm to understand if a certain image comes from a certain source. And suppose you rely only on the histogram. What does this mean? It means that you rely only on first-order statistics. So you want to understand if a certain image undergone a certain processing, but you can only look at the histogram. Does it make sense? Well, it depends on the manipulation. In this example, I'm considering contrast stretching or gamma correction. Given that contrast stretching and gamma correction has an impact mainly on the histogram of an image, then having an histogram-based detector makes sense. So we can study contrast enhancement or gamma correction detection based on histogram by using this theory. Thanks to this, we can avoid the cat and mouse game, and we can devise a universal attack that is optimum based against any detector based on first order statistics. And this is what we do. So this is the attack. This is the optimum attack described in this paper here. So the idea is, you have your original image. Suppose it's black and white, gray level. You process it. So for instance, you apply contrast enhancement. And this is your processed image. Then what you do? The problem now is that you do not have a PX, a standard PX for image that have not been processed. So what you do? You have a database of pristine images. So this data set of pristine images plays the role of the PX. They are examples of probabilities of standard pristine images. Then what you do? In this data set, you choose an histogram which is as close as possible to the histogram of your image after processing. And then you compute the optimum transformation according to optimum transport theory, moving the histogram of the processed image into the histogram you have retrieved from the dataset. And you do this in such a way to minimize the perceptual distortion. And you do this in the, so you first remap the histogram, and then you apply this to the pixels. What you have in the end is an image that has been processed, but at the same time, its histogram is very close to the histogram of a pristine image. And then they cannot be distinguished. Close or equal, it depends on the amount of distortion you are allowed to introduce. If the amount of distortion you can introduce is a lot, you can make these two histograms exactly equal. And then there's no way to distinguish them. Otherwise, they can still be distinguished, but with much more difficulty. Here, n does not go to infinity. So it's not equal 1 or equal 0. So let's make an example. This is your original image. You apply gamma correction. And so you see, this image is very dark. After gamma correction, the image is much, much better. This is the histogram after gamma correction. You can easily reveal that this has been gamma corrected because of the gaps. What do? You have a database of pristine images with no gamma correction. You look for an image into the database whose histogram is as close as possible to what you have. In this case, I came out with this histogram. It's not equal, but it's somewhat similar. It's B model, the average value is the same, something like that. Then I remap my image into an histogram, which now is closer to the one in the database. And this is the best attack I can implement. And the remapped histogram will be similar to the target one if the distortion I can introduce is larger. But I want that the remapped image looks like the gamma corrected image. I cannot go back here, otherwise, no way. And so what has happened here? This is after gamma correction with no counter forensics. This is the histogram in the database, and this is after counter forensics. Now, distinguishing between these two will be very different, very difficult. Another example. This is an image after gamma correction, and this is the histogram with all the gaps. This is an histogram of a pristine image in the database. If I am allowed to implement a maximum distortion equal to 4, I can bring this into this, the max equal to 4, and now these two are much closer. If I judge this to be contrast enhanced, then this other will also be likely to be judged as contrast enhanced. But this is pristine. So since these two have a very similar histogram, it is very likely that I will make an error when I try to distinguish between these two. And in this paper, we ran some experiments and we found that indeed, this is the rock curve without the counter forensic. And you see that the detector is almost perfect. We have an AC, which is, I don't have the name here, but this is close to 90%. No, even more. It's about 95. After the counter forensic attack, the performance drops a lot. Almost a random detector. So you see here I am translating the theory into this practical attack. It's not exactly like the theory, but it's close to it. And you can also give a meaning to the security margin. What is this, the security margin? So here you have an image. So you have a class of images, C0. Good. And they have a data set, a database with images belonging to class C0. Then I have another image that does not belong to this class. It's another class. How much is the security margin between this image and the class of images C0? Good. I consider all the images in the dataset, and I take the one for which the earth mover distance between these two is minimum. And this minimum earth mover distance will be, in a sense, your security margin. Because if you can allow an attack which is larger than this, you can make the histogram of this new image exactly equal to that of at least one image in the database. And then this image and this single image in the database of C0 images cannot be distinguished based on the history. And so, in a sense, this is the security margin, a practical way of interpreting the security margin between this image and the images in class C0. Okay? That's all for the practical part. Here I have another example, but I will speak about this the day after tomorrow. So then I will say a little bit more about an extension of the theory, but basically I'm done. So do you have questions about these practical applications? I hope that now with these examples, things are a little bit easier to understand.
Yeah, I have a question here. What are the other areas where these have been applied? So apart from images, is it applied in videos? Is it applied in networks? So what are the other places where this could be applied?
Okay, personally, I've seen this being applied only in images, but I think this could be applied or have been applied, I don't know, in networks. Because in networks, I mean, it makes sense. I mean, this can be applied whenever a detector based on first order statistics makes sense. So in images, having a detector based on histogram makes sense. In network traffic analysis, this can also make sense because the histogram can tell you how often certain packets of a certain length are transmitted. So I am aware about detectors based on first order statistics. So whenever a first order statistic makes sense, then this theory can be applied. If you rely on more complicated statistics, then it starts to be a little bit more difficult. Good. Let me finish here. So that was the game with perfect knowledge of the sources. We wrote several other papers with some extensions. I will not go into the details here. You have some details into the slides, and at the end of the slides, you have the references if you want. I just give you the definition of the game, because as I told you, defining the game is already very interesting. So suppose now that you do not have, you don't know Px exactly, but you have an example sequence drawn by P of x. So the two sources are not known exactly, but Px is known through a training sequence Tn. I don't give you the model. I give you an example, a very long example. So now I want to understand if xn was taken from P of x, but I do not know P of x. I know only a sequence taken from P of x. And this training sequence is available to both the attacker and the defender. And possibly these two training sequences are different. And once again, the attacker wants to modify xn in such a way that xn seems to be taken from Px. If you think about this now, you don't care more about P of x. The idea is that you receive xn, you have a training sequence Tn, and the question is, are xn and Tn produced by the same source? Now the decision is made not on a single x, but on the pairs xn and Tn. I don't know P of x. So I want to know if two sequences have been taken from the same source. And the attacker takes a yn generated by a source which is different than the one used to generate Tn, and he wants to modify yn in such a way that after the modification, Tn and, sorry, call this Zn. After the modification, Zn and Tn seems to have been produced by the same source, even if Yn wasn't. This is the new game. This is the source identification game with training data. And this leads to a precise definition now. The set of strategies for the attacker is the set of lambda zeros for which the probability that two sources Xn and Tn are generated is smaller than a certain false positive. And consider now lambda zero is defined is a set of Xn and Tn. And the attacker takes Y, he also knows T, so this function F depends on T as well, and it produces another sequence Z such that the distance between Z and Y is smaller than a certain distortion, and these new pairs, Y, T, should fall inside lambda zero. And once again, the payoff is the false negative. The game is much more complicated. We can come out with an equilibrium point, but if I want to say it in 2 words, I can say that everything remains the same, but I have to replace D, the divergence, with a new function, which is this with this H. And what is this H? Is a generalized divergence or generalized likelihood function, which is a linear combination of 2 divergences. The divergence between Xn and the new sequence R, and another divergence between T and the same sequence R. These divergences are balanced by the length of T and X. But most of all, what is this R? R is a sequence obtained by concatenating X and T. This R, in a sense, is the most likely P of X that can produce both X and T. So the problem here is that I have X, I have the training T, but I don't know the sequence, I don't know the source that produced them. Well, the most likely source to produce X and T is a source that is obtained by concatenating X and T and taking the empirical probabilities. This is the most likely source. And then this is the interpretation. When you have known sources, you have P of X, and you care about the Kullback-Leibler distance between your sequence and P of X. And then everything is defined in terms of this. Now, because this distance tells you how likely P of X can generate Xn. How likely is that Xn has been generated by P of X, which you know. In the case with training data, you don't know P of X. You only have Pxn and Ptn, the empirical probabilities of your sequence and your training data. Then, if you concatenate X and T and you obtain this R, this PR is the most likely P of X. So you can interpret this PR as your better possible estimate of P of X. And then you have to wonder, how likely is that this best guess generated both Xn and your training sequence? The probability that this generated X is given by the Kullback-Leibler distance between this best guess and Xn. The probability that Px generated T is the Kullback-Leibler distance between T and R. And then, if you want to know the likelihood that this source generated both, is the sum of these two divergences, these two Kullback-Leibler distances, weighted by the length of T and X. If one of the two is longer, this is weighted more. Then everything remains the same. Your optimum decision is still comparing the distance between Xn and Tn against lambda. But now the distance is no more the divergence, but this generalized likelihood function. This function is famous in statistics. Good. Then nothing changes. You can define, as usual, the lambda 0, indistinguishability region, and so on and so forth. Forget about the slide. And look here. If you want to compare the case of known sources and the case with training data, we know, we can prove that given two sources, P and Q, the H function is always smaller than the D function. So the generalized likelihood is always smaller than the Kullback-Leibler distance. And again, the generalized likelihood function is equal to 0 if and only if the two sources are equal. Because of these two properties, the indistinguishability region in the known sources case is always smaller than the indistinguishability region of the training data case. So the source identification gain with training data is more favorable to the attacker than the case with known sources. However, when the lambda small tends to 0, the two collapses, and the security margin in the case of known sources is equal to the security margin with training data. So from the security margin point of view, the final result of this new game that has a horrible theory, I have to say, proofs are really difficult now. Nevertheless, the final result of this new game is that the security margin does not change. Even if for finite n and non-zero lambda, the case with training data is better for the attacker. But in the limit, the two are the same. So the indistinguishability of two sources does not change if the source is known through training data or perfect. Last slide. We have yet another extension of the source identification game, where now the attacker can also modify the training data. You see it here. The detector must decide between something generated by X and something generated by Y and attack it. But an additional input of the detector is the training data produced by X. But this training data produced by X does not come clean. It comes after another possible attack. So the attacker has also the possibility of corrupting the training data. This game is even more complicated. We studied this in this paper in Transaction Information Theory 4 years ago. Go there if you want the details. There are many versions of the game. The theory here is even more complicated. But now the result is that the distinguishability region depends on the percentage of corrupted samples that can modify. And now the security margin changes. If I can modify the training data, then not only the game is more favorable to the attacker, but the distortion we need to introduce is more.
Welcome to session 2. But this will be my first session for this day, day 1. So as I have just told in the earlier session when Professor Barni was there, that we are going to do it together, so it will go hand in hand. I'm just
Dr. Manish.
Yeah. So the topic,
I think there is some echo which is happening.
Serial signal processing, along with mathematical
No, some of your earlier recording is
working.
Yeah, something is playing behind. I'll just check.
Which will be used tomorrow and day after in many security problems.
Yeah,
this is what he had told.
Just one second.
Summary to what he has done today. I will talk details about introduction to machine learning.
There's a lot of noise here.
Use all these concepts which are being used.
Yeah, there is some issue. I'll just sort it out.
With the Google Colab with simple notebooks. So we are going to look into classification models, CNN architectures.
Professor Barni, you are muted.
Okay, I don't know what's happened.
Yeah, there was some echo, I think. There was some echo with some recording, which this is being live streamed. So there was some echo here.
Yeah, yes, exactly. But it disappeared now, okay?
Yeah, this disappeared now, hopefully. I think it was like an attack on, and we were defending.
It's possible.
Right.
Nevertheless, I'm done. There is that the final result of this further game was that now, if the attacker can also modify the training samples, then the security margin changes, and this is even more favorable to the attacker. But I mean, if you are interested, you can look at the theory in this paper. Last thing, here you have some references. These 5 papers are the papers where we developed all this theory. We developed this theory in these 5 papers across 5 years' time. And all this theory has been summarized into this booklet. This is a booklet of the Foundations and Trends in Communications and Information Theory series. This is 172 pages where we have summarized all this theory into one single booklet, I would say. It's not a book, it's not even a paper, it's something in the middle. So if you can find all this theory, even the games that have not described carefully here, with all the theory, all the math, all the proofs set up very carefully in here. So if you are interested. And of course, if you have any questions, you can reach me by email or in any way you want. Before this, do you have questions about what I said today? I understand that this theory is not easy. It's very perfect, very elegant, everything works, but this theory is not easy. And even applying this in practice may not be so obvious, even if we manage to apply this in some cases. I still think that the case with training data and corrupted training data could be applied to some machine learning stuff, because you see, I started with the case where everything is model-based. So you have a perfect model, perfect theory. Then I started introducing training data, and these go a little bit closer to machine learning because you have training. And then we consider also corrupted training data. So which is a case where you have machine learning and an adversary in front of you that can also modify the training data. The gap between theory and practice is still pretty large, but still there are chances of bringing these two together. By the way, if you consider the paper where Goodfellow invented GANs, he's introducing GANs as a game between the generator and the discriminator. And at a certain point, he looks for the equilibrium point of the game. And this equilibrium point is based on divergence, Kullback-Leibler distance, and maybe even on this generalized likelihood function. So there are ties and links, but that still needs to be explored carefully. I'd like to do that when I have some time, I will. Nevertheless, I mean, this is the theory. I understand it's not easy. If you look at the papers, especially the last two games, they are very complicated. The proofs are not as easy as those that I gave today. But if you're interested and you like this branch of mathematics and information theory and statistics, I guess you will find this very fascinating and exciting. Given this, starting from tomorrow, everything will be easier. So don't worry. The worst part was today, and starting from tomorrow, you can forget about the method types. You will still have a little bit of game theory, but everything will be more practical and easier. So don't worry, the worst is gone.
Professor Barni,
please.
Just I was thinking one question. Can we apply this game theoretic approach to avoid adversarial attack to design machine learning algorithms?
Today, sorry?
To suppose to design machine learning algorithm to avoid attack on the data or some to
I didn't understand the name of the attack.
No, just suppose data sets change. If attackers are able to change the data set and may make the machine learning model make a fool, that suppose you said that cat and dog images, if some false image here she is able to create.
So I mean, in a sense, I mean, if you have a machine learning and you have your training data, machine learning can be seen as a way to compute the posteriors of your data given the class. So you can think about, I mean, one possible approach to interpret machine learning and neural networks is that they estimate the probability distribution of a certain class. Good. And this is learned through examples. So if you are able to modify the examples so that one of the classes seems to be closer to the others, then this can fit into this model that they gave about corrupted training. So if the attacker can change part of the training data, if you look at the slide here, you see that you have that after the attack, you have training data which is formed by two parts. One which is pristine and one which is fake. So in this version of the attack, what the attacker does is that it introduces into the training data some fake samples. This can be seen as the parallelism is that could have a machine learning system where the attacker introduces into the training data some fake examples in order, for instance, to make two classes more similar. Well, there is a parallelism between these two. Studying this to avoid the cat and mouse loop in the end, so to apply the entire theory, can be difficult, but it can give you some hints about how the game will end up if you go on. I don't know if this answers your questions.
So, is it kind of poisoning which is happening to the data?
Yes, it's like poisoning. Yes.
Okay, and so if there is a introduction of a poisoning into the data, can we not retrain the classifier assuming that it is already poisoned?
It depends on what poisoning means. Okay.
So,
depends on what poisoning.
Yeah. So my kind of thing is, can we retrain assuming that our data is not clean? So can we do that kind of approach? It would be a possible defense. It would be a possible defense.
But you need to know. I mean, this will be the subject of what I will say tomorrow and the day after tomorrow. In the framework of this theory,
okay,
then here the detector sees the training data and is labeled correctly. So in this framework, it's not possible to retrain by using the correct labels in this theoretical framework. In practice, you can do it, but this theoretical framework does not take into account the sum of the labels. This tau M2 is labeled poorly. So when you do retraining, the idea is that you have adversarial examples, but then the labels are correct, you know. And then you can retrain with that. Or let me think about this. Well, I mean, yes and no, okay? So what is done in practice, I will speak about this tomorrow and the day after tomorrow, good? In this theoretical framework, okay, if you assume that one of the two sources, the training, so your description of one of the two sources can be modified so to make it more similar to the other source, then you can retrain, but your performance will decrease. So suppose you have cats and dogs, and suppose that in some of your dogs, the real dogs, the dog that are dogs, you introduce some features that look like a cat. So you modify a little bit, don't know, the ears or the tail of these dogs in such a way that they are similar to cats. But still, by looking at these images, they look like dogs. Dogs with some cat-like features. You can retrain your system so to teach the system to understand that these dogs with some cat-like features are still dogs. Good? And your system will be able to do that because it's very clever. But the distinguishability between the class of dogs with some cat-like features and cats, the distinguishability between these two classes will be lower now because some of the doggy features have been replaced by cat features. And so these two classes are less distinguishable. At this point, if you can attack the dogs at test time, the amount of distortion we have to introduce is smaller than before. I don't know if this was clear.
Yeah, it's clear. It's clear.
It is? Okay. So, I mean, just to exemplify it even better, I oversimplify. If I want to distinguish between cats and dogs, I look at ears and the tail only. So I have two ways of distinguishing cats and dogs. Okay? And no, sorry, I look at three things. I look at the nose, the ears, and the tail. Good. Then, in my training data, I have some dogs with tails like cats. But because of the ears and the nose, they still look like dogs. Then I train my system and teach the system that dogs with the tail of a cat and the ears and nose of a dog are dogs. Great. Then I can distinguish. But suppose now that I want to transform a cat into a dog. I don't need to change ears, nose, and tail. It's only sufficient that I change ears and nose. Because if I have something with the ears and nose of a dog and the tail of a cat, the system classifies this as a dog. And so now I need less changes in a cat to make it look like a dog, because I've trained the system to ignore the tail, because the system has been trained on poison data where the tails of the dog is like that of a cat. The general view. Is this understandable?
Yeah. It's fairly clear.
It's very clear. So this is the theory. I mean, bringing this in practice is always difficult, but at least the theory tells you the general view is a way to frame your thoughts and your ideas. Other questions? Okay, if there are no questions, I think we can stop here. I know it's very late in India now, so it's time for you to go for dinner, I guess.
Yeah, it's time now for dinner. Almost it's time. So I think we'll close this session. We'll thank again Professor Barni for joining us. So tomorrow, participants, please note Professor Barni would be joining early, so that he would be joining in the morning, but it would be afternoon for us. So we meet at 2 o'clock India time for Professor Barni's session. But we would be meeting earlier with my collab notebooks in the morning of India time at around 9:30, the time that we started today. So with this, again, we thank and say a namaskar, namaste to Professor Barni, and for the elegant theory that he introduced. And of course, it was his own group which has proposed this particular theory, source identification game. If I could summarize this, it is a source identification game, and it is being measured by something called a security margin. So these are jargons which has been introduced by his group. I know Professor Barni, Fontana, and Benedetta being part of that group, and they have a couple of papers in very good venues. So it was a pleasure hearing, though it was mathematically harsh in the sense that it was a lot of math, but its applicability we would be seeing in many areas that he said that tomorrow onwards it would be more application oriented. So we would like to hear him again tomorrow. So Professor Barni, again, thank you very much. So we are leaving the meeting. So thank you. Bye-bye.
Okay, thanks to you. Goodbye. See you tomorrow.
See you tomorrow. Bye-bye.